technically we are starting in 3 minutes, 2 minutes, but I wrote this 5 minutes ago. Can somebody write in the chat confirming that audio works, video works, things like that? And then we'll wait a couple minutes and we will start. Let me see where the camera frame is. Okay, should be fine. All right. We are ready, but we will wait a bit. That's good. I had a stand for the iPad. I don't know how convenient it's gonna be for me to write today, because I had a stand and I lost it somewhere and I couldn't find it in a couple of minutes, but let's hope this works. Also, in the typical Apple fashion, both my Apple Pencil and my iPad were completely discharged. But at least they charged pretty quickly, so we should be good. Why is this? Okay, all good. Okay. All right, let's officially start the stream. So, at this point, Vulkan 1.3 is kind of old news. I think it was released in, I want to say, early March. But I promised people that I would do a stream about Vulkan 1.3, but I was really not in a good state to talk about Vulkan and things like this for reasons that are obvious to anybody who's been following what has been happening in the world for the last 4 months. But kind of, at some point this had to happen, and I think at this point it would be good for us to resume the normal cadence, normal streams, things like this. So we are going to talk about Vulkan 1.3 today, even though technically Vulkan 1.3 is out for a few months now, so some people may have already had the chance to play with some of the new features in 1.3. But we are going to go through this regardless, because I think that it helps to talk about things not just from the perspective of what they do, which we are going to do, but also from the perspective of why they're there, why some of these features are important, what important problems do they solve, and do these problems need to be solved. It's important to note that, in some of these extensions, I actually participated in the process of sort of making them happen. I was a very loud advocate for at least one of them in the past, but for a lot of other extensions I had nothing to do with this, and so in some cases I'm gonna say, hey, it's not always the case that I agree with the development of Vulkan, but we're gonna cover all of that. So this is kind of the agenda for today. There's sort of a lot of things to go through, but at the same time, I think similarly to when we did Vulkan 1.2, there's a few themes in 1.3 development that we are going to sort of organize around, as in, this is not just a randomly assembled list of extensions that happen to be useful. Some of them are, but a few of them form sort of a couple of groups are forming here that represent larger, interesting topics of discussion and evolution of the API that we are going to talk about. I think we will probably start with, let's start with, so there's at least 2 large groups. Yeah, let's start with one large group, and then maybe we'll talk about a few small things, and then maybe we'll talk about one more large group, and I think maybe there's only 2 large kind of sets of problems that we are going to talk about today, and everything else is smaller. Yeah, I think that's right. So if you have questions, feel free to ask them in chat along the way. I'm going to look at them as we go. And yeah, let's just take it from there. Okay. So the first set of extensions, and we are going to look a little bit at the sort of extension specs and things like that. But the first set of extensions that we are going to talk about today, wait, hold on. Oh, great. Whatever. Are going to be, let me see. So we're going to talk about these two. And these two. Is that it? Yeah, I think this is it for now. There was one more fun thing that I wanted to talk about, but I don't think we can now. We can yet. So people who are familiar with Vulkan and people who are not familiar with Vulkan but are familiar with other APIs like Vulkan, so for example DX12 for Metal, and people who come to these APIs from the sort of background of having experience with previous APIs like OpenGL or DirectX 11 or whatever, one of the big surprises that is shared among all of these APIs is the concept of PSOs. So PSO stands for pipeline state object. I don't remember the terminology. I think it matches across these three APIs, but whatever, there's like sometimes minor deviations. And what this means is that for you to actually render anything with Vulkan, unlike DirectX 11 or OpenGL, where you can say, oh, I need to set a vertex shader, I need to set a fragment shader, I need to set blend state, I need to set like a bunch of different bundles of state. And there is one object that is called PSO that aggregates basically 95% perhaps of the rendering state that you can create from vertex shader, fragment shader, and then like geometry shader, tessellation evaluation shader, whatever these things are called, task shader, mesh shader. Are we done yet? Or let's not talk about ray tracing. Uses slightly different concepts. I think this is reasonably comprehensive. I probably forgot something. So given this large array of shaders and given vertex layout, as in what components of the vertex are there, blend state, depth state, call mode, I don't know, like MSA modalities, like some bits around this, and a bunch more. There's like a very, 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 very large struct. It's probably the largest struct in Vulkan that you will ever have to deal with, that has all of this data. So you put all of this data in, and then you say I want to create this thing, and out comes an object that you can then apply. So I think it's important to talk a little bit about kind of how we got here, because some of the extensions that we're going to talk about are going to be difficult to understand without this. So the way we got here is that in other APIs like GL, DirectX 11, etc., you would set all of these pieces of state individually. There's minor deviations. So in DirectX 11, you create a state object out of some of these small bits. Like blend state is actually 5 parameters, and instead of setting 5 parameters in DirectX 11, you create an object that aggregates these, and then you set this object. And in GL, there's extensions, but without the extensions, you create like a program object that holds the shaders together. But none of these things are actually important. All of these things are just like API craft around the core concept, and the core concept is you set a lot of state individually. So one of the biggest problems with this comes with the fact that in real hardware, some of the state interacts and, how do I put this? In some GPUs, there is not a hardware block that can be set up to control the vertex layout. Instead, the knowledge about the vertex layout is baked into the vertex shader. So then when you have an API where you set vertex shader and vertex layout independently, you have odd set of choices. You can dynamically create or patch the vertex shader, like create the program binary that actually fetches data from the correct sort of places in memory and correct formats and things like this. You can try to create like two shaders and sort of execute both of them. One like first execute some sort of vertex shader, pre-vertex shader, let's call it this. I don't want to call it by the real name. That grabs the data from the vertex buffers and then execute the real vertex shader. Some hardware doesn't know how to do this, so there's like complications. One other complication that is pretty famous is that on some hardware, some mobile hardware, there is no blend stage. Instead, blending is part of the fragment shader, where fragment shader can actually read the fragment, modify it, and then write it back. And so when you set fragment shader and blend shader individually, again, you have to combine them in like a single program. There's complex interactions around like geometry shader, tessellation shader, like all of this stuff is getting really complicated. And then sometimes, for example, maybe you want to have vertex shader and fragment shader, and instead of compiling them individually, you compile them together. So you have this API that doesn't match how the hardware works. And what happens then in the hardware is that you do all of the state setup before Vulkan. And then you say draw. And when you say draw, the driver knows all of the state and it tries to figure out, okay, what do I need to do? Do I need to create some new shader binaries? Do I need to assemble some state packets in some complex way? Because maybe in my GPU instruction set, there's a single command that sets simultaneously depth and call state, and so I have to merge these somehow, right? And so this has to happen at draw time, because before draw time you don't know the state. And some of this work can be expensive. And so what would happen is, for example, you set state, you do the draw call before Vulkan, and then the first time you do a draw call with this particular state combination, it takes like, I don't know, 10 milliseconds for the driver to actually process this draw call, instead of like less than a microsecond. But then the next frame you do this, it's fine because the driver has cached the combination. And for the application, there was no way to control this. There were weird workarounds that we won't talk about. So this was a little bit of a mess, right? And this was a problem for graphics developers because they said, hey, our application has stutters that we cannot remove because the driver does a bunch of work behind our back that we can't control. So then here comes Vulkan. Vulkan says, hey, no worries. Here's all of the state. You can create the pipeline object. Then you set it, and then you draw. And we're going to do all of this important work that needs to happen, that is GPU specific, etc., when you create it. And importantly, it's on the application to make sure that this creation happens during a loading screen, or basically the application should expect that creation can take a long time. Draw does not take a long time, and the application should budget for this. And if the application has a lot of pipeline state objects, then this takes a lot of time in aggregate, and so the application should also minimize the number of pipeline state objects that they create. So this is how this concept sort of was born, right? And again, it's shared between DX12, Vulkan, Metal. There's some deviations in details, but so it turns out, while it is possible to use Vulkan in this perfect way, where you pre-create all of the pipeline state objects with all of the combinations, and then at draw time you just bind them and draw, it is difficult. It can be difficult. There's basically two problems. There's maybe three problems. So one problem is sort of the engine architecture problem. As in, hold on, let me, okay. When Vulkan was created, I mean, the assumption was you're just gonna target Vulkan with your graphics engine, and maybe you're just creating one from scratch or whatever. Of course, the reality is people ported existing engines to Vulkan. So then you take an existing abstraction layer that's inside your engine and then try to make it work. And to actually introduce the concept of the pipeline state objects in earnest, you have to propagate it all the way down through your, all the way up through your, wherever up is, through the graphics stack. It has to be like end to end, as in your, I don't know, your like asset system has to support the notion of being able to store the pipeline state descriptions for, it's complicated. Like there's a lot of pieces that have to fit together for you to actually fully embrace PSOs. It's doable, but in some cases it's difficult to rework the engine based on this. The second problem is this mismatch. So I'm gonna call it the PSO combinatorics problem. And the issue is, so even before Vulkan, many games, many sort of like large, extensive graphics applications, not just games, right? I don't want to focus entirely on games, but games first and foremost, had the problem of that's called like shader combinations explosion. As in, when we talk about these vertex shaders, etc., 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 what actually would happen is that you don't have just a few vertex shaders. You have like tens of thousands of vertex shaders and tens of thousands of fragment shaders, and tens of thousands is actually, you know, it's a decent number because some games would have hundreds of thousands. And the way this would come about is that you would have a shader that can do a lot of things. Maybe you have a fragment shader that is the material shader for your game, and your material shader has like 20 different things that it can do. It can apply, it can have a normal map and not apply a normal map. It can have a emissive. It can have a emissive that's a single constant, like a color. It can have a emissive that's a texture, etc., 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 etc. And then in the shader, you would have, for example, you would use the preprocessor, so you would have defines for every important part of your shader, and so you would have like 20 Boolean defines. And then this results in 2 to the power of 20, which is a million potential combinations. Some early games, Crysis was famous for this. Crysis kind of started this. Crysis? Far Cry maybe? I want to say Far Cry, not Crysis. Kind of started this whole thing because it was, I think, the first famous game, at least, that actually did this compilation from defines at runtime, and then they would have a QA pass that would go through the entire game and try to pre-record all of the combinations that are actually used in practice. But so, like I said, you have 20 Boolean parameters. That's 2 to the power of 20 potential combinations. That's a million. It is unlikely that you actually use all of them. But you do use some of them. And so there is this general problem, which is that you want combinatorics, and the number of total possible permutations that you have is very, very large, like millions, tens of millions. I think Unity has the system, and they have the system where you can specify this Boolean constants per game, like for shader. And I think they used to have a limit of 64, if I'm not a Unity person, but I think they used to have a limit of 64 Boolean parameters. So that's 2 to the power of 64 combinations. And then I think there were 2 times when they bumped it, once to 128 and once to 256. So I want to say that today Unity probably supports 2 to the power of 256. I don't even know what this number is. It's like a very large number. That's potential, theoretical computations. Like none of this fits in computer memory, none of this you can compile, actually, etc. And so the problem is that it's really difficult to convert. It sometimes is difficult to convert this set to a very small set that you know ahead of time, which Vulkan wants you to do. for complex reasons. Like some of this stuff may be controlled through user settings, some of it may be controlled through some runtime gameplay parameters, etc. So this was a problem even in the shader land. But part of how people dealt with this problem is they said, okay, let's decompose the problem. For example, our vertex shader and fragment shader are two distinct shaders. And maybe we have 20 parameters or something like this, right? So you have, hold on. So you have, let's say, total of 20 defines, and so that's 2 to the 20 combinations. That's around a million. But people would say, okay, but let's look at these parameters. And actually, for example, we can structure things such that maybe 5 of them control the vertex deformation process, which happens in the vertex shader. And then the rest 15 only control the fragment shader. And we'll structure things such that the vertex shader always computes some data that's sufficient for the fragment shader to function. And so instead of this, you would go to 2 to the power of 5 plus vertex shaders plus 2 to the power of 15 fragment shaders. 2 to the power of 15 is 32,000. So that's like you reduce the number of possible permutations 30 times. And that actually is maybe practical now to precompile ahead of time, all of these, right? You can't do this anymore in Vulkan. I mean, you can still do this in the shader space, but if you wanted to pre-create the PSOs, you can't because the PSOs merge these. And of course, it's worse than this because what about vertex layouts? What about blend states? What about depth states? What about cull states? Some of this knowledge you can bake into the material system inside your engine, but some of this is really difficult to bake into it. Which brings us to our third problem with this whole thing, which is that there's this mismatch between the PSO model and the hardware model in that some of the way PSOs were designed was to take all of the state and bundle it together. For every individual GPU, actually a lot of the state that goes into PSO isn't hard to decouple from the whole blob, right? And so on a lot of GPUs, what happens is these extra PSO combinations that you have to create, they are excessive because the GPU doesn't actually require them, like solving the problem of frame spikes when you create the actual driver state didn't necessitate bundling all of the state together. Of course, this is where we get into a difficult conversation because on one hardware, vertex layout is merged into the vertex shader. On another hardware, it's not, but the blend is merged into the fragment shader. Some hardware maybe wants to know about the cull mode or something when compiling the vertex shaders because it's like a tiled architecture and so it has extra binning stuff that it has to take care of. And I don't know, there's like complications, and because Vulkan is designed to target the largest possible set of hardware, it runs into this problem where it can't confidently say, oh, this piece can live outside of the pipeline state object because no hardware that we care about will ever want to separate it. But this is a problem for the graphics applications that run on top of Vulkan because it makes the combinatorics problem worse because you have to bundle all of the state together, even though it didn't need to be the case. One of the very common examples that many people run into is this notion of very simple task of object mirroring. So imagine you have a render engine, and for every object you can specify the rotation matrix and translation and scale, but the scale can be negative. So you can scale the object by -1, in which case it flips around. This is super useful for for level designers because they can reuse a lot of objects that they have by just like mirroring them, putting them in different places. The problem is to mirror an object that is not sufficient to just flip the scale, which is just a transform. You also have, at the minimum, flip the culling mode from back face to front face because the culling flips. But color mode is part of PSO. And so now you have doubled the number of pipeline state objects that are required to render objects in your game because you support mirroring, which is especially a big problem if mirroring is something you want to support at runtime. Like gameplay code can flip an object, mirror an object, because you can't even. This is the number 2 problem that I was talking about, where there is a mismatch between the potential combinations and real combinations. So anyway, this is a huge headache. For all of these reasons, it's a difficult problem. And because of this, different engines decide to take different paths. So this is an evolving space, as in the specification of Vulkan today, 1.2 didn't adequately solve this problem, 1.3 doesn't adequately solve this problem. There are some graphics engines for which it's fine. id Software's id Tech 6, 7, I don't know what the number is at this point, is famous for this because when Doom Eternal, Doom 2016, when it came out, they made a presentation of SIGGRAPH, and I think they quoted something like under 1,000 unique pipeline state objects, which if you've ever worked with Vulkan, under 1,000 is an impressive number for an engine like this. So it is possible to design an engine around these limitations, but a lot of engines find themselves in this difficult spot where it's really hard to deal with. So with this long preamble aside, let's talk about the actual things that happened in 1.3 to make this problem a little bit more manageable. It doesn't, without fully solving the problem, but it's a little bit more manageable. We will talk about dynamic rendering later on the stream. So the specific extensions I wanted to talk about in that space is extended dynamic state. You will note that there are 2. And this stuff. So the first big problem that I noted, this is a good overview. So the first, let me increase the zoom level. Hold on. Oh no. 1 second. Okay. So the first part of that problem that we talked about was, hey, PSOs aggregate a lot of stuff, including state and shader setup. And in some cases, the state is something you want to toggle dynamically, and this makes the permutation problem worse. This is interesting because I remember the exact same conversations that happened in DirectX 11, because DirectX 11 introduced the rasterizer. It introduced the state objects that like aggregated small bundles of state together. Sometimes there would not be a driver representation behind them. Sometimes there would be. These were somewhat expensive to create, but not on the order of milliseconds. But still, there were emissions there. Like some rendering algorithms require, I think, a reference value with a stencil state, and maybe that was forgotten. Maybe that was DX12. Like this is a reoccurring, essentially, problem, right? Where the hardware vendors and the API designers say, hey, it would be nice if everything, if the API knows all of the state together, and the application developers say it's actually very inconvenient. So there's 2 extensions now with which you can configure your pipeline state objects to pull some of this state out. So we talked about the object mirroring problem, right? Where you have to flip the culling. Well, now you can make it so that your pipeline state object doesn't specify the culling, and instead you specify it separately. Culling in Vulkan is like, there's like 2 things. One is the winding and one is the front back, but they're technically redundant for the most part. And so with this, you can flip like one of these things independently from the PSO, which is actually sufficient to implement mirroring. So you can say front, you can say back separately. This is important not just for mirroring. For example, I don't know, when you render shadow maps, There's cases where you want to flip the depth order from like front to back and back to front for different light objects for like complex reasons. Again, before this, you had to create a new pipeline state object. Now you can extract the state out of this. And you will see it goes on and on and on. Depth comparison, depth tests. You can set front face separately. This is weird. Okay, whatever. Primitive topology is another one. Yeah, so if you want it, even in Vulkan, if you want to render objects, for example, if you want to support triangle strip meshes in Vulkan, which there's questionable utility in them at this day and age, but there are certain cases where you kind of want this if you're running a memory constrained environment. Like there's cases where you might want to do this, but it's baked into the pipeline state object. Like whether you use triangle lists or strips or whatever, I think is baked into the pipeline state object. And so let's see if and so if you want to render like both with the same draw call, you can't. If you wanted to draw points using the same vertex shader that you render everything else with, you have to create a separate one, etc. Like there is classes of use case where it's inconvenient to have this inside the actual shader. So now you can separate that. And then like scissor tests, stencil tests, viewports. So there's some state that you can now put aside. The viewport thing is weird because, with count. Right. This probably relates to the case where you want, there's certain cases in VR and in shadow map rendering where you want to render into sort of multiple viewports, and this is probably related to that. Again, you don't have to create multiple state objects. So the curious part is that there is this extension which is called extended dynamic state, and there is also, did we open it? And there's also extended dynamic state 2. This is one. The browser is failing me. Which adds a couple extra things. This is more enabling depth bias is useful at runtime. Logic ops there's so few applications that use logic ops that probably the only reason why they even have this here is like, hey, most GPUs don't support this, and GPUs that do can just, which presumably are NVIDIA GPUs, can. So like there's no reason not to. Primitive restart is something you might want to enable. This if you use triangle strips, then you may need to enable primitive restart. But if you unconditionally enable primitive restart, you actually pay a GPU performance penalty in some cases. And so in some, like sometimes these go together, but this is more minor. I think most of the applications that want dynamic state would either be satisfied by this list or be not satisfied by either. For example, you will note that blend state that I was talking about is not in this list and not in that list. And the reason, to my knowledge, there's not really a problem with toggling blend state dynamically for like desktop GPUs, let's call it this way. But there is GPUs in the mobile space where blend operations are part of the fragment shader. Or actually, even NVIDIA has this weird extension that can specify like 25 different blend modes that come from Photoshop. And I don't know if they actually support all of this in hardware earnestly or not. Anyway, so there may be complications with blend states on desktop. There's definitely complications with blend states on mobile. I think, unless I'm mistaken, I think Vulkan 1.3 requires that 1.3 compatible GPUs support this. Yes. This is important. Some of these core promotions, some of the features that made themselves into the Vulkan 1.3 come with no strings attached, as in if you declare that you require Vulkan 1.3, you can rely on these features and which is great because you are making a rendering engine for Vulkan 1.3, you're dealing with this PSO problem. Like, you don't have to solve the problem of culling mode as part of PSOs if you target 1.3. Some of these features are optional, presumably, like this one, right? Yeah. So we're gonna maybe call it out when some of these features are optional, but the dynamic state is required, and so you target 1.3, PSO management got a little bit easier for you. So there's the second set of 2 extensions, which are more complicated to talk about. Why does this whole Zoom thing is okay? And let me reopen this one. So we talked about the states, but states are only part of the problem, and the dynamic state extension only allows you to pull some of the state out of the PSOs. Like, the problem is very large, and so these extensions help a little bit, but they don't solve the problem. There's 2 other extensions that also don't solve the problem, but maybe they help a little bit. That touch on the part of the problem, which is, so if we go back to the issues, right? So there's like engine architecture problems, PSO combinatorics, etc. So in some cases, the solution to all of these problems, for example, with dynamic state, is to carefully optimize your PSO combinations, carefully restructure your rendering engine, etc., 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 such that you know all of the PSOs at the start of the game. Which is great. If you can do this, you probably should. However, even then, though, there is like this small problem, which is, okay, so it's not clear what number is good enough. As I mentioned, Doom claimed that they used like under 1,000 PSOs, which is a really good result. I would guess that complex games require like hundreds of thousands combinations. There is scary tales that I will not share about like worse situations. The problem is, though, so imagine you actually do have 100,000 PSO permutations. Is it reasonable to create them all before the game starts, like during loading screen? Well, it takes time. It can take a lot of time. Vulkan has this concept called pipeline cache, which I will not talk about. You can read a blog article that I wrote about it on my blog. If you have never been to my blog, then you should stop by. Although I don't write much there at this point, but maybe I will resume at some point. So there's like a blog article there on pipeline caches. Even with pipeline caches, 100,000 is like a lot. Before the pipeline cache exists, like at the first start of the game, you will have to create all of this from scratch. This is a pretty bad user experience. There are some games that have shipped on PC that I will not call by name, but I played some of them, let's put it this way, where like you start the game and it like has this, I'm gonna compile all of the shaders for you screen first time you start, and the screen is up for like 15 to 20 minutes, which is pretty ridiculous, because that's a lot of combinations. In one of these cases, the game could do this in sort of background, kind of, but they had some bugs with the cache, and so every time you would launch the game, it would start recompiling them from scratch. So like, anyway, it's not clear that you actually want to compile 100,000 permutations ahead of time. Ideally, you wouldn't have 100,000, but what if you do? And what if you have an engine that can support this, etc. So there's like complications with this. One extra complication is, so I talked about this setup where you have a shader that has like 20 booleans, right? 20 boolean defines. In Vulkan, there is a specialization constants, which is a core feature from 1.0 that is an alternate way to deal with the same problem that doesn't require preprocessor work, but it's the same problem because you have to specify the values at PSO. So you have 20 booleans. A lot of them are actually optimization booleans in most cases, as in they don't flip the behavior such that you have to set it to 0 or 1, otherwise the object doesn't render correctly. It's more like you can set it to 1, in which case the object will, for example, apply emission. But actually, the rendering engine can bind the emission texture to like a black 1 by 1 pixel texture, which is going to cost performance on GPU, but the object is going to render just fine. So practically speaking, in many cases, out of this permutation space, there's like a large portion of the space which is optimized shader permutations that you technically didn't have to use, but if you don't use them, your GPU frame time will be larger, so you want to use them. For all of these reasons, there is cases where even in an authentic Vulkan application, you actually want to know, is this bundle of state, like is this set of permutations of PSO, how long will it take to create? Can I wait for this long? What happens when I ask the driver to create this PSO? Does it compile microcode? Does it just patch some bytes somewhere in some existing structures? Is this operation very cheap or is it very expensive? Because what sometimes you can do if you know that creating a PSO would be very expensive is to simply fall back to a different, more general version of the same PSO that enables all of the possible features that you have. Then in background, on the background thread, compile a more efficient version of a PSO. And then when that is done, on the next frame, when that is done, start using the new one. Which then, instead of the user waiting for like 20 minutes compiling shaders, what actually happens is the user plays the game instantly. But for example, maybe the game runs at like 40% slower sort of GPU frame time for the first, I don't know, minute, until the most important shader permutations get recompiled, and then the application transparently substitutes them, and then things are very fast. So this is the theory behind kind of what is possible, what would be possible in Vulkan. But to do this actually efficiently, you have to have a little bit more information about what happens when you create a PSO. And so because of this, there is these two extensions which I think are motivated by broadly like this space. So for example, when creating a PSO, you can ask, hey, if you're actually going to compile shaders, which is the long part of the creating the PSO that takes like forever, like tens of milliseconds, just tell me that you just like fail the pipeline state compilation process as early as possible. Just tell me that you could do this, but it would require a shader compilation, so you don't. And then I can do the same operation on a different thread asynchronously and not disrupt the gameplay. There is also, in some games, there's maybe cases where you can just afford to not render the object at all until the pipeline state object compiles, which will result in it appearing like later than usual. But if you have a streaming system where objects appear as they're loaded from disk, then maybe it's okay to just show them later instead of creating a frame spike. So this is the motivation for this, right? And there's also some pipeline state synchronization stuff, which is like pretty trivial. I won't cover this. So this is an interesting idea. I would imagine somebody will try to use this. I don't know how practical this is really, because it's a sort of, there's a lot of looseness around this extension. How long does the pipeline state object take to create if it doesn't have to compile shaders? Who knows? Should you still pre-create a bunch of the stuff early? Who knows? But at any rate, this allows you to essentially say, okay, before starting the game, I will compile everything that I have to compile, and then everything that's like optional and these optimization style constants, I am gonna ask if I need to create them, because, for example, maybe they are already cached in the pipeline cache. And if not, I'm just going to do this in background, however long this will take, and, things are going to be fine. So this is the theory. I don't know how practically useful this is, but this is trying to help with this general problem of the PSO management. So the second extension is in a similar vein. But it gets even more complicated to argue for why this is useful. And I will have to talk about what base pipeline states are, and I hate the concept. Maybe let's just skip this extension. It's in the same vein. It's like trying to give the application a little bit more information, but this time about how effective the pipeline cache is. I don't know, again, how practically useful all of this is going to be, because I think the real difficulty around the PSOs, you kind of have to solve this at a higher level, regardless of what the solution is. It's a little difficult to make it work really well if you can't at a very high level say, either I'm reducing the PSO count, or I have, hand wave, alternate methods of managing the state, or like it's difficult to sort of patch this later. Anyway, so this is the general PSO story. As you could probably note, this is an evolving space. So we talked about a couple things that help, with the problem. They don't solve the problem, because the problem is difficult to solve, and I am expecting more things to happen in the future. But this is the thing that, so DirectX 12 struggles with this problem. Metal struggles with this problem a little bit to a lesser extent, because Metal has a little bit more. Metal has simpler PSOs for two reasons. One is they don't have some of the features that make the problem even worse. Metal doesn't have geometry or tessellation shaders, and so like their shader space is literally half of the Vulkan shader space, which is good. And they move some of the states, such as I think depth state, cull state, and a lot of other stuff, out of PSOs, and this was the case from Metal 1.0, because they had a smaller set of hardware that they targeted, and they said, for this hardware, we know that we can comfortably set all of this stuff ahead of separately from the shaders. But fundamentally, all of these APIs share this problem, which there's no great solution for as of yet. All right, so this was the first big topic of the day. I am going to switch to a few smaller things before we tackle the second big topic. But let me first look at chat. This is not chat. Chat is happy, or silent, or some combination thereof. Let me look at this. This looks like a long list, and it feels like we've only gone through 4. But a lot of this stuff we will just talk very briefly about. Really, there's 2 remaining big topics, not 1, 2. Each of these is 1 extension, and a bunch of small stuff. Let's go through a few small things. Let's actually go from, this is cool. So 1, 2, 3, 4, 5, 6, 7. This is, okay, let's go through like 5 or 6 of these, because I just want to say like 2 words on each, because there's not like, it's not a lot of interesting stuff that I can say about this. Let me switch to this. So, Vulkan 1.3 adds yet another extension to do like a different version of YCBCR, which is a video-friendly color format. So you can now create a texture with this format and use it if the GPU supports it. Cool. Like, not interesting. I mean, maybe interesting if you're doing video. Not very interesting. I don't know why this... Oh, this is promoted, right. So this is a weird case where, okay, similarly to the previous one, so there's this format called STC. It's a block, I think it stands for Advanced something texture compression. What is S? I don't know. Something texture compression. So this is a an analog for block compressed formats from Direct3D, such as BC like 3, 4, 5, 6, 7. It is more general and way more complex. So like Direct3D block compressed texture formats all have blocks 4x4. STC has blocks that are like 7x7 and stuff like that. The encoding is really complicated, etc. But there is this texture format, right, STC, which is very complicated, but it's good if you ignore the complexity, as in you get good quality textures, you get a lot of freedom as to how you want to balance the bitrate versus the quality, etc. It used to be that there were no encoders that were like useful in production because everything was really slow. Now there's a thing called STC Enc. I think this is this the one? Not actually sure. I don't. Yeah, I think this is the one. Maybe. I feel like I may be confusing this. I feel like there might be a different one. No, I think this is the one. So it used to be basically that encoders were really slow. Now there's encoders that have that run at good performance, and most importantly, on mobile hardware, you don't get support for any of the Direct3D block compressed formats, which is sad, rather sad. Instead, what you do get support for is ETC 1 and 2, which is okay. 1 is pretty bad, 2 is pretty alright, but 2 is pretty alright if you have color textures or sort of normal maps as well that you want to compress. If you have HDR textures, you're out of luck. If you have high standards for color accuracy, you're out of luck, etc. So STC solves this problem. If you're targeting mobile, you probably want to look into this. And there is a format, STC HDR, which is high definition support outside of 0.1 with block compression. It was previously available as an EXT extension. So to use it, the driver had to support the extension. It's now available in Vulkan 1.3, but it's optional to support, meaning that instead of the extension, you now get a boolean in the features struct that says, oh, we support this format. And so practically speaking, for any application, this extension, the promotion of this extension to 1.3 changes very little, because you had to figure out a strategy for supporting devices that don't expose this anyway, because this is optional. And so this was the thing that I was talking about earlier, where some features in 1.3 are required, which makes things much simpler for you if you target 1.3. Some things are optional, which makes things like a little bit easier, like you don't have to use an extension, but practically speaking, not a whole lot changes. Anyway, so this is that. We are just gonna skip this. It's like minor. Did I promise to talk about literally every single thing? I think I'm just gonna skip things where there's nothing interesting for me to say, because this is like, you can allocate textures slightly more optimally on some hardware. I think it's NVIDIA authored, so presumably it's NVIDIA hardware, because like the alignment specification that the driver can tell you is now a little bit more precise, but it's like not very significant in this scheme of things. So this one is a little bit interesting. We're going to talk about this a little bit. This we're going to just skip. So this allows you to attach extra custom data that your application manages to Vulkan objects, which often is not a big deal. Like, unless you're writing a Vulkan translation layer or something like this, not translation, even some sort of extra layer that sits between the application and the Vulkan driver, you probably don't care about this, because any data that you wanted to associate with Vulkan objects, you can usually associate it more easily with your own like wrappers around Vulkan objects. So we're just gonna skip this completely. So we are gonna talk about this, but maybe a little later, because I want to talk about that and this, and maybe that's it. But at the same time, because it requires a little bit of exposition of some GPU stuff that some people may not be aware of. So we're gonna skip that. So there is this two, I believe. Why there are two? So there's these two that are a little bit interesting, just to like, it's a good excuse to talk about some complex specification problems. Yeah, so this is for this one. Yeah, and this one. Okay, yeah, so let's talk about both of these. The problem is pretty trivial and pretty, it's a little bit stupid, but it's like, it's the reality of what you have to deal with. And we are gonna get two extensions with one stone. Somehow, it's interesting that the list of contributors is very different. Two of them are the same, but for some reason this, oh, is it because this is the GLSL one? This is cool. Okay, so what is this about? There's these two extensions, 1 and 2, that all they do is they add one each. They add one extra command to the shader bytecodes, PRV. But they are connected because they are talking about, oh, this is adding, oh god, okay, I see. All right, we're gonna just skip part of this because it's tricky, but they are talking broadly about the same feature, the same problem, which is the discard and fragment shaders. So this is where I will need to talk a little bit about. All right, let's just go there. A lot of these extensions are take time to explain, not because the extensions themselves are complicated, but because there is somewhat critical background knowledge required for some of them, which is kind of the point of this whole series. So we will have to go and talk about this. So let's just do that. So people who have written shader code in HLSL or GLSL in the past for any graphics API might be aware of the fact that in the fragment shader you can say discard. What discard does is it terminates the processing of this pixel, and it results in this pixel not being written to the output. This is something that, for example, you can use alpha test for, which you could do before shaders existed. And then like Direct3D 11 killed alpha test, I guess. So you had to do this in the shader, but there's cases where you want to do this in the shader regardless. So this is useful in a variety of places. Maybe you want to do dithering, so you want to randomly kill pixels based on some specific, or pseudo-randomly based on some specific grid pattern. Maybe you're writing a shader that can allow you to sort of see through a part of the object, and for this the only reasonable way to do this is to actually go to the fragment shader and in the fragment shader compute some function, some distance function, and like kill the fragment, right? So there's a host of reasons why you want to do this. So typically in the shader you would have something like if some condition discard. I think it's like a statement, so you just do discard with a semicolon. So this seems straightforward. And indeed, since Vulkan 1.0, this feature was supported, and there was an instruction in the fragment shader that is called kill, that kills the fragment. What happens is it doesn't get written to the color buffer, it does not get written to the depth buffer, and whatever happens in the fragment shader after this generally also doesn't happen. But this is where things get complicated. So What is probably not a surprise to a lot of people who are watching this, but what might be a surprise to some, is that GPUs always process pixels in groups of 2 by 2. The actual groups are larger. So let's not, for people who actually know what I'm talking about, you can probably find flaws in my simplified explanation, because I'm not trying to be very accurate about this. But you start with a grouping of 2 by 2, let's put it this way. So this is called a quad. For obvious reasons, it's 2 by 2 pixels. It's always pixels that are adjacent to each other. They might be aligned to like 2 by 2 grid, they might not be aligned, but like it's always pixels adjacent to each other. This is very important. And so what happens when you rasterize a triangle is that instead of finding all of the fragments that we need to run fragment shader for, instead we find all of the quads that the triangle overlaps, and then we run the fragment shader for all 4 pixels, all 4 fragments in the quad. And actually the grouping is larger because these quads then are merged into like a superstructures that we are going to talk a little bit more in context of other extensions, maybe, or maybe not. Maybe not. Let's just assume it's quads. So this is a interesting, is my camera view overlapping this? Hopefully not. This is an interesting general problem in the GPU space, because the fact that you have quads is critical because quads are used to compute derivatives. You can differentiate any expression in the fragment shader because you always have the neighboring pixels in the quad, fragments in the quad, so you can just do the delta, what's it called, like difference-based, basically, a differentiation by subtracting like 2 computations from each other, and that approximates your derivative. And this is important because derivatives are used to compute MIP levels, and MIP levels are important to fetch textures. And so unless you don't use MIP maps at all, you have to have this feature. And because of this feature is kind of non-optional. Like even if your fragment shader does no texture fetches, it will still be organized in quads. And this is a problem because this actually can result in loss of efficiency. Because if you have a triangle that's very small, that only overlaps 1 tiny pixel, you actually still have to spend the effort of shading all 4 pixels of a quad that it's in. So normally you have this computation in 4 fragments of the quad, and they happen simultaneously, let's put it this way. At any point in time, you can say, oh, I have an x, which is a variable that I computed somehow in the fragment shader. Maybe x is the wrong, let's call it t or something. At any point, you can say, I want to compute the derivative of t in the x direction and screen space x direction. What this actually means is it is going to take t from 1 pixel in the fragment, in the quad, and t from another pixel in the quad, and just subtract 1 from another. And this can happen implicitly, sort of, I'm simplifying a little bit, but this can happen implicitly as a result of fetching from textures. For this, it's very important that t is available in both fragments, and really in all 4 fragments of the quad, because you can also take the y derivative. So it's all good. The question is, let's say one of these fragments got discarded, but the other one didn't. How do you compute the derivative of t that is computed in another fragment later if the other fragment got discarded, which means it never computed anything useful? And this is fun because, of course, there is 2 APIs, Direct3D and GLSL, and Direct3D and OpenGL, and 2 shading languages, HLSL and GLSL, that have specifications for discard. And of course, these specifications differ. One of them says, I don't know which one, it doesn't matter. One of them says, After discard, all other fragments still exist in the quad. Oh, sorry, after discard my fragment, the fragment that got discarded still exists in a quad, and it's still being processed. All of the computations are still being run. The only thing that doesn't happen is if it like outputs data to buffers that are not the color buffer. It can't output to the color buffer or depth buffer because it got discarded, but it could still have instructions that write data to memory someplace else. Like these don't happen, but the computations still happen. And this means that in other fragments, you can do these derivatives, you can compute these derivatives correctly because the computations still happen. It's still fine. The other API of course says, no, actually, nothing happens in this fragment, which makes derivatives undefined in other fragments of the same quad. So this is a problem because some applications assumed one behavior and some applications assumed the other behavior. One behavior is like more efficient because you don't have to spend the processing time. The other, but so like one behavior is more efficient and more surprising. One behavior is unsurprising but inefficient. And there was no way to distinguish between the two. And now there is. My guess is that this extension, like a lot of other extensions, is motivated by the increased adoption of Vulkan in translation layers. If you got yourself a Steam Deck, then what probably happens when you play a game on Steam Deck is that you're running a Direct3D application that uses shaders compiled for HLSL that assume the HLSL semantics, that then get translated to Vulkan shaders and get run via a Vulkan Linux driver on your Steam Deck on whatever AMD GPU is there. And so some of these little corners of the API that were easier to brush sort of aside before now get more prominent because there's a lot of applications that expect very specific behavior, and you can't change these applications anymore because they were compiled to like a Windows binary that you now run on your Steam Deck. You can't like ask the developers to build a special version for the Steam Deck because translation layer doesn't do something. So I'm guessing this was what motivation was, but maybe not. At any rate, now essentially when you're compiling a shader from GLSL or HLSL source, you can actually assume the correct semantics as long as you're targeting Vulkan 1.3. Assume the correct semantics of what discard actually means in specifications of both of these languages. I have no idea what Metal does with this, but all right. Let me cross some things over so that we don't forget stuff that we have covered. And maybe let's talk about another big topic before going further with smaller things. So we talked about this. We talked about this. Oh, we didn't talk about tooling info. Tooling info is also boring. So we are leaving this for later. Talked about this, and this. All right, let's see. Finite differences, thank you, yes. This is the differentiation method. This is a thing that you like don't think about until you start asking yourself questions. Or somebody asks you questions, like in an interview context. But yeah, it is non-trivial to compute the MIP level. Like you have to know the derivatives. And it's kind of funny because it wasn't like a big problem before programmable shading. With programmable shading, it's a problem because, of course, you can... The texture coordinates that you feed into the sampler can be computed using completely arbitrary formula. This formula might not be analytically differentiable, like, at all. It also might have discontinuities, which for some people is a surprise. Like sometimes the fact that you have to do this and the fact that you use finite differences, I guess it doesn't matter that you use finite differences, but sometimes this thing catches you off guard. One of the common problems that I'm sure lots of people ran into is let's say you sample the texture. I'm using like the syntax that is 15 years old probably, but whatever. Let's say you sample a texture and you pass it a fraction of some formula. So fraction, you don't have to use the fraction because you can set it up in the sampler, but let's say you do. What happens is that the fraction is discontinuous. So the function looks like this. And you can compute the derivative of this function at any point except for exact integers, right? So like here, 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 my lines don't align, but you know, hopefully you understand what the function looks like. What actually happens as a consequence of this is that if you are shading this pixel, the derivative that is going to be computed from this is using, the real answer is like the function can't be differentiated at this point, like it doesn't have a defined derivative, but the hardware has to compute one regardless, and so the finite difference method just subtracts the value in the next pixel from the previous one, and so in these cases it subtracts 0 from 1 and gets like -1, right? Or 1, like it doesn't, only the absolute value matters. Whereas at any other point, it would subtract two values that are really close together, and it would get a value that's like 0, 0, 1 or something like this. And so as a result, the MIP level that gets used during sampling the texture at this point is very wrong. And you get weird visual artifacts, and then people try to figure out how to fix them, and then the answer is you have to compute derivatives yourself and then pass it to the texture sampling thing. Anyway, so there's surprising cases where the finite difference method bites you because the function actually doesn't have a defined derivative, but by and large it works pretty well, except that we now pay the price of this any time. There's good blog articles from various people that were written about this point, because the cost of this quad shading can be significant. And it could be avoidable if the hardware, like if there was hardware that could, if you could disable, which is not very easy, but if somehow you would have hardware that could disable the quad aggregation and just run things like in isolation, you could build some rendering algorithms that could take advantage of this and run faster. But, you know, it's difficult. It's a difficult problem because the expectations of most applications are that you can just compute derivatives. All right, so yeah, this is why I don't. Yeah, tooling info is not like there's nothing much to say about this. Let me scroll back to the list of extensions. Okay, so do we talk about synchronization now? Do we talk about dynamic? Let's talk about dynamic rendering, and then talk about a bunch of smaller topics, and then talk about synchronization. Synchronization is like a little bit, it's interesting. It's less interesting than the other two big topics, but it's also a little difficult. So I don't want to, it's difficult to explain because synchronization is difficult to explain in general. So yeah, let's talk about dynamic rendering. Can I, maybe I can go here to fill the space better. Okay. All right, so we talked about PSOs, right? PSO is one big concept that takes people by surprise when they go to these graphics APIs, and this is one concept that can be difficult to adjust to if you especially have an existing rendering engine. The other concept in Vulkan that is even more difficult to adjust to, especially because it is absent from all other rendering APIs, it is unique to Vulkan, is the concept of render passes. So I'm assuming people who watch the stream know what Vulkan is, right? So I don't have to explain it, what render passes are, but I think it would help to explain the motivation again behind passes, right? So in all other APIs, what happens is, including Metal, which some people think render passes exist because Vulkan targeted mobile hardware. And this is true to an extent. Like, I think absent mobile hardware, render passes wouldn't have happened. But the connection isn't as direct as you would think, because there is this other API called Metal that also targets mobile hardware that happens to not have render passes. But in all other APIs, including Metal, the structure of the frame is either that you set the render targets and then you draw. This is what happens in Direct3D 11 and 12 until 12.4 or something, that introduces I want to have a different name for this, because Direct3D 12 has render passes and Metal has render passes, but that's a completely different feature. I don't know what a different word would be. Let's call Vulkan render passes Vulkan render passes, so that we are unambiguous, because there is important distinctions. So, or you, I guess Metal doesn't call them render passes, and they just say begin encoding or something. Anyway, or you can say I want to begin rendering to a render target, draw, and end rendering to render target. These may seem equivalent. They are not quite equivalent. For example, in Direct3D 12, what you also say is you say clear render target. And also after the draw, you may say resolve if you're using MSA to convert from the MSA samples into the sort of single sample per pixel. In Metal, you don't say clear and you don't say resolve. They are kind of embedded into the begin and end. And it's a little bit similar in Direct3D 12 later versions. So Direct3D 12.4 or something like this introduced render passes. The motivation is the fact that you can now buy a Windows ARM tablet with a Qualcomm GPU that is a mobile class GPU, so it's a tiler, so it needs like for efficiency reasons, it needs a little bit to handle these things a little bit different. So this is how other APIs work, right? The important problem with these APIs are tile-based GPUs. So specifically mobile tilers. Tiling is now an overloaded concept because desktop GPUs reportedly have tiling support. Intel is quite upfront about, I think they added that in Gen 10 or Gen 11 or something like that. They're quite upfront about the fact that they now have a separate vertex stage where they run your vertex shader again and stuff like that. NVIDIA's and AMD's tiling looks and works very differently. So the concept is now a little overloaded. But when we talk about the mobile tilers, what happens is your frame gets split into rectangular units. Every rectangular unit is rasterized one at a time. It's rasterized into an on-chip memory buffer, as in the color date and the depth date is rasterized into an on-chip memory buffer. And once the whole tile gets processed, this whole buffer is copied back to main memory. And then you go to the next tile. If an object spans multiple tiles, the object will get rasterized in multiple tiles, or the triangle, not really the object. The object classification is usually... People who come from Xbox 360 background probably have PTSD right about now around like predicated tiling and stuff like that. But so sometimes you do object-based classification, but in newer APIs you don't. I think you just do triangle-based classification. The reason why tilers do this is that your main memory bandwidth could be, I don't know, like 10 gigabyte a second, and your tile bandwidth could be 100 gigabyte a second, even on a low powered like small device. So there's an order of magnitude difference, and so when you talk about blending and operations like this that are bandwidth intensive, you really want to do them with fast memory. So the problem with this immediate API is that when you say clear render target, there's an assumption that it clears the main memory buffer. What happens if you clear before every draw? It kind of breaks the whole tiling sequence, and so because of this, tilers want you to say begin and end. And if you want to clear the render target, you want to have here instructions to clear. And then what will happen is, instead of having a distinct clear operation, you will render one tile at a time, and before filling the tile with triangle data, you will in on-chip memory, you will clear the tile, and then you will render triangles. Similarly, resolve can be embedded here. So what happens is you render an MSA into an MSA buffer, tile by tile. For each tile, you potentially clear the tile, then you render a bunch of triangles with MSA. Then in the tile memory, you do the resolve from the 2x2 MSA 4x to 1 pixel. And then you write that 1 pixel back to main memory. And so the result of this is, instead of having, typically when you think about MSA cost, you think, oh, I need to fill much more memory with data because for every pixel I now have 4 samples. And there is bandwidth optimization techniques that desktop GPUs use to deal with this, but this is the mental model, right? Well, on tilers, the mental model is, yeah, you have 4 times more pixels, but everything is inside this on-chip memory that is super fast. And so actually the cost is very small. And what is critical is that once you render the MSA buffer on chip, instead of having to copy the whole MSA buffer back to main memory, which is expensive because you have to do this slowly, you resolve on tile, you convert 4 pixels into 1, and then you store 4 times less data back into main memory, which is the same amount of data that you would have to store if you didn't use MSA. As a consequence of this, MSA on mobile can be rather cheap, which is good because mobile screens are getting larger, and like some MSA tricks are important in certain cases to balance fidelity. Anyway, so this is how the world looks like outside of Vulkan. And you would think that this is enough you would think that Vulkan should have went with one of these approaches, right? They could have done what Metal did. But the other consideration that Vulkan had is, okay, so we talked about the basic case of storing data on chip while rendering into one render target. What if you want to store more data on chip? What if you want to do deferred shading that has, let's say, 2 distinct passes, between 2 and 3? The correct terminology for what I want to talk about, I think, is deferred lighting, not deferred shading, although the terminology there is very conflated. But what if you have 3 distinct passes? One is you lay down your G buffer. 2 is you, so this writes albedo, normal map, or normal data rather, and I don't know, like specular data. It's very, very, very simple, and depth, of course. So you lay down your gbuffer pass, then you do your lighting pass, which ignores albedo but uses normal spec. It may ignore spec. It needs roughness, but you would bake the roughness into the normal. Let's just say, where's my eraser? Let's just say there's no spec. So it just reads normal and depth, and then produces lighting diffuse and lighting specular. And then you would have the third pass, which is just like a full screen quad, which actually does the shading, where it reads all of the data written beforehand and then produces the color. So in Metal or in Metal 1.0, you have to save the G buffer to memory, and then you have to read it from memory, because like you have three distinct render targets, three distinct sets of render targets, three distinct shaders, sets of shaders, etc. Like you can't merge them all in one thing. So this is expensive if on a system where main memory bandwidth is like 10 times smaller than the tile bandwidth. So Vulkan really wanted to solve the problem and to allow you to write the application such that you can fit this complex algorithm into on-chip memory without talking about tiling. Nowhere in Vulkan specification, to my knowledge, let's see. All right, we had a brief interruption. Okay, there was a brief interruption. Can people comment in chat saying whether we are back? I think we are back because YouTube says so. I don't know what happened, internet blip or something. If you do no sample operation. Okay, cool. Thank you. Yeah, so if you don't do any, like the quad structure works regardless of what you do in the fragment shader. This is how GPUs are built and sort of written. I don't know, I assume a lot of this is baked so deeply into the hardware that you have to print like a new circuit board to be able to like disable this. I don't know. But yeah, it doesn't matter if you do samples, it doesn't matter if you do derivatives. And you are correct, when you have a small triangle, you pay the cost regardless of whether you technically have to pay the cost or not. So, right, so nowhere in Vulkan specification is there a mention that maybe there is, but Vulkan doesn't have like an object, Vulkan doesn't have a way to ask, is your GPU using tiling? Vulkan doesn't have a way to ask, without maybe some extensions, what the tile size is, right? So I mentioned the screen is split into these smaller units, rectangular blocks, regions, right, that are rendered one by one. What is the size of this? Vulkan will not tell you as an API. So Vulkan hides this concept from you. But Vulkan wanted to be the API that allows you to... some people talk about Vulkan as a low-level graphics API. This is actually incorrect. I think I'm not being controversial when I say this, because I think people who work on Vulkan implementations and Vulkan API agree with the fact that low-level is a misnomer. Vulkan isn't a low-level API, it is an explicit API. What this means is that it wants the application to tell the driver in as much detail as possible the intent of what the application is trying to do, and then have as much freedom in the driver as possible to implement this intent on the hardware efficiently, which is a laudable goal in general. Like it makes sense why Vulkan went in this direction, because if it worked, it would be great. And so, right, so as a result, Vulkan exposes to you the render passes, which hopefully people know about, which allows you to say, hey, I want to create an object that will tell the driver that I have three subpasses, the gbuffer, lighting, and shading, inside my overall render pass. Gbuffer will write to these four textures, lighting pass will read from this two and write to this other two, shading pass will read from all of them except for normal, I guess, and depth. A shading pass would read like albedo spec and lighting diffuse and spec and write the color in the basic setup. So have the structure, tell the driver about the structure, and then the theory is this. So let's actually fully write this out. So shading takes albedo, specular parameters of the material, and then the results of oops, sorry, let me move this again. The results of diffuse and spec lighting passes and output color. And then you actually might have tone mapping and stuff like this, but let's just ignore it. So this is the basic vanilla setup. So the what the hope is that the driver will say, okay, you have the structure. For every pixel within a tile, I need some amount of memory to dedicate to that pixel throughout this entire process. Let's think about how this could look like. So you need albedo, I will just abbreviate normal, spec, and depth in the first pass. So we'll need to write these out. Then you will need to read normal and depth. And then you will need to write lighting diffuse and lighting spec. But for example, you won't need the normal for that pixel in the future because you will never use it again. You will still need the depth for like reasons. You actually might need the normal because maybe you will re-render the same. Actually, ignore me. You will read the normal. So in the second pass, you will read this 4, and then you will write light diffuse and light spec. In the final pass, you will read albedo, spec, diffuse, and light spec. You will write the color, but you don't need another storage for the color because, for example, you're not using the normal buffer in the third pass. So let's just say that you will write the color here. You actually don't need the depth. Some of these are different byte sizes, but whatever. Let's just bear with me. So you need 1, 2, 3, 4, 5, 6. Let's assume that all of these things take 4 bytes, which could be a reasonable assumption depending on whether you want HDR or not. So 6 times 4 is 24. So this needs 24 bytes per pixel. And the driver can say, okay, cool. I have, let's say, I don't know, 30. This is an under. This is a low estimate, low bar. But let's say I have 32 kilobytes of on-chip memory for a tile. I need 24 bytes per pixel because I know the entire algorithm, right? Which means that I can process more than, let's round down, let's say I can process 1024 pixels. This is a 32 by 32 grid. Which means that I can split my screen into tiles of 32 by 32 pixels and then do the whole process for every tile, all 3 passes, all 3 sub-passes. At the end, get the color, and then repeat. Everything is on chip memory. The only thing that goes to main memory is the final color output. Super fast, beautiful, works great. Crucially for this algorithm, every pixel only ever needs to look at the result, at the contents of the data inside that pixel. And because of this, Vulkan, as part of this whole subpass infrastructure, introduces not just the ability to tell the driver about every individual thing, but also a new way to read data from textures. So instead of sampling textures, you have this concept called input attachment, which you can get data from in the current pixel in the fragment shader. And that's kind of it. So this is why this exists. The theory is you tell the driver about this whole pipeline. The driver can very efficiently, you have to tell the driver about all of the shaders involved in this pipeline. Or rather, for every shader involved in this pipeline, you have to tell the driver that this shader will be used in that setup. Because the driver may have to synthesize special code that when you read from input attachment, it says, oh, hey, okay, you're reading from light diffuse. Light diffuse is the component number 5 in my tile pixel data. Cool. I will give you data from component number 5. But to know that it's component number 5, you have to have laid out the entire render path into a series of microcode instructions, or you have to have done the whole thing to actually be able to know what does light diffuse mean in the fragment shader that does the final shading pass. So you tell all of this to the driver up front, it synthesizes all of the shader, bytecode, microcode, etc. efficiently, it generates all commands, it renders everything is very fast. So this is the theory, this is why it exists. And if you run on a GPU that is not tile-based, from the exact same instructions, the driver makes very, very different decisions and arrives at the same pixel output, but without having to go through this process. For example, it actually allocates the textures, it actually stores everything in the main memory, etc. So you write your application once, you tell the driver explicitly what you want to happen, what result you want to achieve. The driver decides exactly what happens at the low level and makes it happen. This is why the API is explicit, it is not low level. The running joke is that you also need to use a lot of explicit language when using Vulkan, which is also why it's an explicit API. So this is why Vulkan render passes exist. This was really important to talk about because we need to talk about why it's actually a false promise. It happens often that I talked about this many times on streams before. You may have read many articles about this. There is this problem with abstractions, which this is an abstraction, which is that they leak. They may hide too many details, and what details they try to not hide, these details still bleed through. Let's talk about the problems with this whole setup, right? So like I told you, the ideal scenario that should happen. There's also things that you can think about. For example, if you have MSA, then maybe shading doesn't resolve MSA. If you have post effects, oh no, low power mode, it hopefully will live through. If you have post effects, then you might have more than three subpasses in this render pass to post-process the result that went through MSA resolve, etc. So the thing on screen may seem complicated, but it's actually the simplest viable example of like subpasses in Vulkan. The real examples are more complex. So what's the problem with this? There's many problems with this. One big problem is that you don't know, because the API is explicit, not low level, you don't actually know what happens in the final hardware. And even though you hope that the things that I told you that should happen will happen, you don't know that they will. You don't know that you're going to have 24 bytes per pixel to store this data. Maybe you don't. So maybe this whole process breaks down, and instead of compiling this optimal set of shaders, the driver just gives up and says, I can't do this. Which feels like a driver problem, but it's actually your problem, because you have designed an algorithm that you thought would perform optimally on the target hardware, and it doesn't. You might run into just implementation bugs, which was actually rampant in the early days of Vulkan with these complex features. Because if there's no production applications using this complex setup, then the first production application that does, turns out things don't work. There were lots of problems with MSA around subpasses where multi-subpass MSA resolve didn't work correctly, etc. So there's like just bugs all over the place because this is complex. You are very restricted in the amount of things you can actually do. For example, you have a GPU that has 32 kilobytes of on-tile memory. And I told you, well, 24 bytes per pixel, 32 by 32, so that's like 24 kilobytes of data per tile. But you have 32, so you have an extra 8. Could you store some extra data that is not mapped like pixel to pixel there and access it? For example, one other deferred lighting sort of approach is what's it called? I'm blanking. The forward plus, but what's the so like there's a technique called forward plus where you build an acceleration structure that allows you to go through the light list. I don't know if it has an official name, like voxel volume, I don't know, whatever. So there are some cases where you want to structure your frame such that instead of just every pixel having the contributions that are left by some draw calls, you have this extra lookup structure that you can consult to get the list of lights that affect a few pixels, not just every pixel, but like a smaller tile of pixels. You could store this in the on-chip memory in theory, like it would maybe fit there, but the problem is that you don't know what on-chip memory is. The API doesn't tell you. The API tells you you have a pixel. For that pixel, you can look at the data written to that pixel by previous subpasses, nothing else. What happens if you want to look at other pixels above and below? There's some problems with this concept because you don't have access to the pixel above you in the top pixel of the tile, which there's ways to work around some of this stuff by like, there's ways to work around some of this stuff, but you don't even get access to this because the only thing that you get is the current pixel. So whenever you want to ask, oh, can I reduce the resolution of some intermediate target in the setup, you can't. It's impossible. You can scale the whole thing down, or like pixel addressing modes will break down. Whenever you build pixel shaders or pipeline state objects, you have to tell the pipeline state object in its creation, which is the thing we haven't talked about this entire render path structure. That makes the pipeline state management problem way worse. Because we talked about shaders and states previously. These are all things that are ostensibly can be thought of as like material setup in the engine. But now you have to tell the PSO about your entire frame structure, or as much of it as fits into a render pass, before even building it. What happens if this subpass structure changes? For example, if you want to incorporate post effects into this render pass, what happens if the post effect configuration changes dynamically, which can be common? I don't know, maybe you have a radial blur, and the radial blur only activates if in a racing game your car is like not idle, or you have like some gameplay effect applied like boosting, or maybe you have different sets of tone mapping, like shaders that get selected based on, not shaders. It gets complex to talk about some of the more complex examples because you get to talk about the very specific render pipeline of a very specific application. But like there's many cases where you want to dynamically alter the structure of your frame, which in Vulkan, if you do, it affects your render path configuration. And as a result, it affects every single pipeline state object that interacts with that participates in that, I should say, which makes it intractable. Like you kind of have to have this specific fixed frame structure settled for the render pass before you start creating pipeline state objects. And we just talked about the fact that you want to create pipeline state objects before you even start the game, really, right? And so this locks the whole thing down to an extent where it also makes a lot of choices of the rendering algorithms impractical because they just don't fit into this very, very, very rigid structure. And the worst part, of course, is that if you don't care about stuff like that, if you only have a single subpass in your render pass, you still have to go through all of the ceremony to set this up. Because when the Vulkan API was designed, they said, hey, we want a single way for you to do stuff. This single way has to solve this important problem of mapping rendering algorithms to a tiled architecture. Therefore, this is what we are going through, and everybody who uses Vulkan has to go through that. One thing I didn't talk about is nowhere here have I mentioned compute shaders. The reason I haven't mentioned compute shaders is that you cannot integrate compute shaders into this structure. They have to be like separate. And so this is another example of how this render path setup is very rigid. It only allows you to do a very small set of things. in hopes that this set of things can be optimally mapped to every target hardware. This substantially restricts your set of algorithms that you may want to use. This locks you down because of the API restrictions in a very fixed frame structure that is really difficult to alter dynamically. And the mapping process to the low-level details breaks down in practice. And all of this affects every single user of Vulkan, whether they care about any of this or if they want to just render a triangle onto a render target. So this is why the render passes, in my opinion, and the extension exists, and my name is on it, but it's just one of the many names on that extension. This is why Vulkan render passes aren't the optimal, I don't want to like judge. It makes sense why they exist, but effectively it doesn't solve the problem. And so because it doesn't solve the problem, a different solution was required. All right. I want to take a break of a couple of minutes. I want to plug my iPad because it now has 9% charge, and if my iPad dies, all of the beautiful illegible text on the whiteboard is gonna, well, not disappear, but we aren't gonna continue doing this. But I think I've set up the problem of why render passes aren't good enough very sort of extensively. So we're going to talk about dynamic rendering, which once you understand all of this, the dynamic rendering portion of this is very simple. So we're going to go through this and then go through the rest, but this is going to be after a couple minutes. I need tea, and I need a break, and I need to plug an iPad. And you can feel free to ask questions in chat. During this, I will look at them when I get back. A render graph abstraction, right? We haven't talked about render graphs. Yeah, so the biggest issue is that I don't. Render graphs often come up as a way to manage synchronization, which they are a good tool for. We will talk a little bit about synchronization at the end as part of one of the extensions. You can imagine a render graph framework that is Vulkan specific to the extent that it can assemble the render passes yourself or for you. It does require changing the shader code often. You might be able to manage this. Changing the shader code doesn't have to imply that the framework has to dynamically build the shader code or like assemble it, but you're gonna have strict restrictions on this. But render graph, the problems that we've talked about, let's maybe enumerate them. They aren't solvable by the render graph abstraction, except for the problem of it's just a pain to work with all of this, right? Oof, hold on. Oh my god, no. Okay, I just want to charge you. Why are you not? Oh, it says, what the heck? It says not charging. Apple. Will it charge if I plug it? Oh, I can plug it into the MacBook, right? Thing about Apple devices is that somehow every time I need to use an Apple device, it doesn't have charge. I used my Apple Pencil last time on stream, like 3 weeks ago, and it was fully charged. It was at 0% today, despite the fact that I haven't used it. And this is my general frustrating experience. Any Apple device that you leave, like, not plugged to a charging thing is just gonna discharge quickly, and I don't know why that's a problem, but that's a problem. Okay, so it is charging off of MacBook, which is great. Let me reconnect this, and then we will continue. So let's enumerate the problems, or let's write them down. Some of what some of these like we talked a little bit on the high level about all of this stuff. Some of the accusations against the render pass model that I have are they require substantiation in the sense that I make these claims about like algorithms not being compatible with this and like what are these. We will not do this. Obviously, a lot of this was taken into account when deciding to actually go through with the extension. But let's write the problems down. Am I in the right place? Hold on, I'm lost. No, I'm not lost. My whiteboard disconnected. Oh my god. Is the chat connected? The chat is connected. We will talk about metal. The whiteboard connection broke. Technology. Hold on. Okay. Hallelujah. Okay. All right. So let's quickly re-summarize what are the problems, why are render passes problematic. So one, it imposes rigid frame structure. It makes PSO management worse, like dramatically worse. I think it's easy to underestimate to what extent some of these just like dramatically complicate how you deal with some of these design issues, because they force you to connect systems on a high level in the engine that just have nothing to do with each other, like streaming system that deals with assets and like I don't know, like a post effect system, and like you can plug them in through one giant render graph abstraction, but it doesn't actually usually help enough. So it's very limited with respect to actual like functionality. Like I mentioned, no compute. You have to access the same pixel of a target, so there's problems with multiple resolutions and stuff like this. There's like a bunch of other things like that. It impacts every user of the API, because you have to use this regardless of whether you want to or not. Like you have to connect your PSOs to render passes actually, regardless of whether you want to or not, and stuff like that. There is also the implementation. Implementation concerns, let's put it this way, as in there's issues with driver implementations. You can't be certain that you're actually going to get an efficient rendering sort of setup because the driver may decide that it can't support this. You get no feedback about this, like things like that, right? And let's just leave it there. Let's just leave it there for now. So the point number 4 is fairly important, because like it doesn't matter if you have a render pipeline that doesn't require this kind of tile reuse, or if you have a renderer that never cared about mobile in the first place or tilers in the first place. Like you still have to kind of buy into this render pass thing. And right, so the render graph abstraction, it fixes 4 as a byproduct of like hiding all of the complexity behind a hopefully much nicer interface. It doesn't really fix anything else, right? Because you're still limited with respect to functionality. You're still not sure if the render graph is actually optimal or not on a given piece of hardware. Like these are not theoretical concerns. These are very practical concerns. For example, one use case that is often cited that is much simpler than deferred shading of the subpath structure is a custom resolve. So you have a 2x2 MSA and you want to go into the non-MSA. And the question is this arrow, this aggregation operator, what does it do? Does it just average all 4 colors? If it does, you're in luck, because you can just use the fixed function hardware for this, which Vulkan exposes. Do you need something else? Well, you need a shader. How do you use a shader to go from a 2x2 to non-MSA target? Well, Vulkan allows you to do this. You just bind the MSA thing as an input texture. You read 4 times. You do the computation. You write it. That's a bad idea. That's a bad idea. That can be a bad idea on immediate GPUs actually, because it doesn't always result in. It requires very complex driver gymnastics to be able to actually read data directly from the compressed MSA implementations, representation that a lot of immediate GPUs do, and this doesn't always work. Let's put it this way. So like this might not work out on immediate mode GPUs, but this definitely doesn't work out on tiled GPUs because you have to save the MSA buffer to memory and then load it from memory in a shader. So this is expensive. So the theory is that you can actually do this operation with a custom shader with the render path structure because you are only interested about the current pixel. You're just interested about the different samples of the current pixel, and input attachment do support MSA. However, I don't know what the current state is, but for the first, basically while I was involved in Vulkan, I would occasionally discuss this topic with a specific graphics vendor, and they would consistently tell me that this doesn't work on their drivers yet. Like, as in, you can try to do this subpath structure, and it will actually just flush the whole thing to memory and then read it back. And that's a big deal. Like, you don't want to ship a game if you know that a very large class, a very large subset of your customer base will have to pay for MSA with this enormous amount of memory bandwidth. Like, you just don't do a custom resolve at this point. You just change your high-level algorithm because you can't rely on this being efficient. And this is the essence of number 5, right? So these are not theoretical concerns, and random graph abstraction doesn't help with this. It doesn't help with 3. It doesn't help with 1. It just spreads 1. Or it could help with 1, sorta, but could help with 2 sorta, but like realistically it just hides 1 and 2. It doesn't fix these, right? So so these are all problems. Now there might be Vulkan games that use this feature regardless of the fact that these problems exist. Like, I'm not claiming that this literally doesn't work. I'm just claiming that people who say that render passes are the answer are wrong. They're not the answer. And in fact, they are not a great answer. But they do work some of the time. So how do you deal with this problem? This is a complicated... I don't have solutions for this problem because... Or I would claim I have solutions, but not everybody would appreciate them because they imply certain things that you may not ascribe by. One of the core problems I claim here is that by virtue of making an abstraction that was designed such that you had to implement the algorithm once without knowing about the tiling at all, and just describing the algorithm to the driver and having the driver figure it out, it is such a big leap. There's such a big gap between the intent and the implementation that the desire to do that is the problem, is my claim. You can disagree with this. It is I can sort of back it up, but at the same time, you could sort of argue that you can solve this problem. Yeah, the gap is big, but look at all of the other software in the world that jumps gaps way larger than this one with other abstractions. But my claim is that this is kind of the reason why we are here in the first place, is that the ask was unreasonable. The ask to structure the algorithm such that you can tell the driver about this very complex setup and then have the driver perfectly synthesize an optimal representation was unreasonable. Some people will disagree with this, which is fine, but I think this is the issue. And the second issue is that because of this ask, everybody is forced to sort of play this game, right? Like, it complicates the life for everyone. It doesn't simplify the life for anyone. So what do you do? Well, I think you do 2 things. You first address number 4. How do you address number 4? Well, you address number 4 by saying none of this complexity is warranted if render passes have only one subpass. Because when you have only one subpass, you don't need input attachments. You don't have these broken expectations about what an API will do, like you're rendering into a target. This is the thing we know how to do well. It is an abstraction that basically doesn't leak. And it may feel very limiting, but the reality is it's not worse. It's hashtag not worse, because the reality is, to my knowledge, most production Vulkan applications only ever use one subpass in every render pass. So like the reality is that by having a mode where you have one subpass per render pass, you are helping a very large fraction of your user base, because this mode can be better. And while you're not fixing the problem, you are fixing the consequences of the solution to the problem that doesn't work, if that makes sense, right? Like you're unbreaking the situation by getting back to the drawing board in an efficient manner, which is what VK-KHR dynamic rendering is. In a sense, it's much closer to what Metal or Direct3D12 has to say about this, which is also great because if you have an application that targets Direct3D12 and Metal and Vulkan, with dynamic rendering, your expectations about what the API looks like are consistent. You can start rendering to a frame to render a set of render targets. You can end rendering. Between this, you have drawing commands. For tiling efficiency, it is important that you can clear when you begin. It is important that you can resolve when you end. All of these features are still supported by dynamic rendering. You don't have to maintain render pass objects. You don't have to talk about render pass objects. They don't exist. When you create pipeline state objects, you don't have to talk about the render pass. You have to talk about a slightly different thing, which I will mention. But it is consistent across all of these three APIs. This gets Vulkan back to the drawing board in a sense, but it also equalizes it with the standard sort of in the industry around this, right? Which, again, when you talk about single subpass render passes, it is better in every possible way, I would claim. It is better on the users as in it's easier to use. It is more compatible with other APIs. It is easier to make a nice abstraction around this so that it's super trivial to use Vulkan to render to stuff. And it doesn't hurt performance-wise any use case where before one subpass was enough. It also doesn't solve the problem. It forces you to use one subpass per render pass because there's no render passes. So it doesn't force the tiler issue. But we're going to talk about this in a second. Now let me look at chat and then we'll look at the extension for like 1 minute because there's one thing I wanted to mention about this. And then I'll talk a little bit about tilers. Okay, so the actual extension, let me close this, the actual extension. Oh, this is super nice. Actually, I'm actually surprised, but this is super nice because there was no way to do depth resolve in early versions of Vulkan, and then they had an extension, but I guess it's now required to be supported, so this is super cool. Anyway, this is cool. This was a big thing that was missing, but it's small. Basically, in Vulkan before, you could say I'm gonna bind this render target as an output. You could say I will write to it, or you could say I don't care what happens to it. You couldn't say I will not write to it, but please preserve it as is. It's kind of an important distinction because on a tiler, when you say I will write to it, the tiler will store the data from the on-chip buffer to the main memory at the end of the pass. When you say I don't care what will happen to it, you're giving the driver a license to completely scrap any memory in the main memory buffer that this thing had, which often didn't happen in practice, but this is the promise that you're like giving to the driver. And there's cases where you wanted to, I don't know, read from depth buffer but not write to it. So it's bound as an output, but you have to preserve the contents, and there was no way to ask to preserve the contents. You had to ask to store the contents. So this is neat as well. But the actual extension. Where is the actual link? So effectively, previously they were CMD begin. The extension does two things. So one is, instead of CMD begin render pass and end render pass, you now say begin rendering and end rendering. So you still have the begin and end, but you don't have the render pass objects. When you say begin, I think end is just no argument. Yeah, end is no arguments. When you say begin, you still have to tell everything about the structure of the render pass. You have to say how many targets you're rendering to. What targets are these? Do you have depth output? Do you not have depth output? For a attachment, you have to say load, store. You have to ask the driver to clear. All of this, or resolve, right? We talked about both of these. Like in Metal, begin has clear implied in it if you ask for it, and end has resolved implied if you ask for it. All of these are important because when you have the single subpass render pass, it's still important for you to be efficient with respect to tilers, which means it's still important for you to not clear as an explicit operation. We talked about this before, and every Vulkan tutorial mentioned this. Don't use the command that clears. Use the clear that's part of the render pass. Now there is no render passes, to use the clear that's part of the begin rendering. But it is way easier to set things up like this. Though the other example, dear God, like Roblox has so much of this. When you want to resolve to a different texture, previously you had to create a render pass that has the texture you're resolving from, texture you're resolving to. This is a little bit of a nightmare because you are tying the lifetime of these two objects that are sort of independent into a new object, and you have to like make sure your objects are destructed in correct sequence, etc., 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 etc. None of this is important anymore. You can say, I want to begin rendering. When I begin rendering, I want to clear stuff. When I end rendering, I want you to resolve stuff with the flags into this other texture that I told you nothing about previously. All right, so this massively, like, you still have to fill weird structures, but you can make wrappers for this, and this massively simplifies the high-level flow, because you don't have to prepare stuff to be able to render to it, you just render it. The other big thing that this kills is the frame buffers. Frame buffers were almost killed. We probably talked about this in 1.2 stream. There was an imageless frame buffer extension which almost kills frame buffers, but not completely. I think this kills frame buffers for good. Good riddance. You want to render to 2 color targets and 1 depth target. You just ask the driver to render to 2 color targets and 1 depth target without having to like create weird objects that like tie them together and all of that stuff. So this is the first big thing that changes. The second big thing that changes is the PSO bit, right? So one big problem with render passes is that when you created the PSO, you had to specify the render pass. This is replaced by this thing, I believe. Yeah. It is tempting to say that this problem is, the PSO connection is fixed for good. There is one thing I wanted to mention because this is crucial. Again, it's shared by all rendering APIs. It's the thing that you can't easily get away from. So when you create a PSO, you used to have to specify the render pass, and you now have to specify this thing. Instead, you don't have to specify the render pass. What this thing says is the format of every render target that the shaders will write to. And if you get the formats wrong, you will have like validation errors and things will not work and stuff like this. For example, this means that if you have a single fragment shader that can output either to an HDR buffer or to a single definition buffer, you have to have 2 PSOs. One has the VK format for like, I don't know, RGB16F, and the other one for RGB A8. So this is the thing that you still have to specify in your PSO structure. The reason why this is critical, and we haven't talked about this, but so we talked about some GPUs in the mobile space that maybe you don't care about, that have blend unit like absent, and instead Fragment shader does blending. Well, the other thing that the Fragment shader might have to do is do the format conversion. As in, the Direct3D 11 assumption is the Fragment shader outputs a 32-bit floating value or vector of 4 values as color, and then there's this magical output merger stage that actually stores these blends, etc., into any format that you can render to. That's actually not how a lot of hardware works. A lot of hardware says, well, we're going to have like instructions in the Fragment shader that like convert the data, and then the output merger will not have the facilities to convert, to do the format conversion. Often it's not like every format is different. It's like there is 2 or 3 classes of formats that are different, and so shader does a little bit of conversion, and then some actual bit packing happens later. But for this reason, when you are building the PSO, depending on the output format of the color targets, I'm less sure about depth. I don't know offhand. I mean, I guess if the shader outputs depth, something similar might happen. But so because of this, when you build a PSO, some hardware may need to assemble the Fragment shader microcode based on the specific format that the Fragment shader writes to. And so because of this you still have to specify in your PSO. It's much less of a pain than specifying the whole frame structure or the render path or whatever. Often you don't have this format ambiguity, like often, you know what format you're rendering things into. It can be a little bit of a pain still. I don't think there's format compatibility rules on this thing. So I'm assuming somewhere it says they have to match exactly. It probably says so in the begin. It's probably validation usage somewhere here. I don't want to fish it out. So I'm assuming the format. I guess I can look for this, right? Maybe. No, I cannot. Oh well. So it says here sample count must match. Where does it say something about formats? It must say this somewhere. All right, I don't know, whatever. So somewhere here there must be a thing that says the formats must match exactly. So there is like cases where this is annoying. For example, when you do HDR rendering, there is several formats that you might want to use. The obvious format is R16, G16, B16, A16 float, or whatever the Vulkan enum is for that. There is a couple other formats that are useful. For example, one other commonly used format is R11G, 11B10F. So it's half the size. The top format is 64-bit, this one is 32-bit. The 32-bit format has like a weird structure because it doesn't have a shared exponent, unfortunately. So it has very few mantissa bits and exponent bits for every component. So you might see visible banding from this, but there is ways to combat this. And there is cases where maybe you want to switch between the two. Roblox has a case where I think it switches between something like this somewhere, but I think it's on a platform basis, not like dynamically. And then there's also a format that everybody should support writing to, but almost nobody does, except for Metal, I want to say, which is R9, G9, B9, E5. This is the perfect format for HDR. It blows my mind that desktop GPUs can't like render to this format. But if there are ones that do, this is like the optimal format, and so you may want to decide between this or maybe the top one. But some of these decisions can be made just based on, like, you don't have to make a lot of this dynamically, so it's still okay. But like, this is the one complexity that remains, and that part of complexity is ingrained into the problem. Like, GPUs require the format to be able to render to it, because some GPUs may require knowing the format when they compile the shaders, because the shader does some format conversion. Like, you can't get away from this problem. So this is something that remains. Other than this, this is a major big news, major simplification of Vulkan frame structure and dealing with all of this. The one caveat, as I mentioned, is it doesn't solve the deferred shading on Tyler's problem. Like, it solves problems that were created in an attempt to solve the deferred shading or tiling problem, which I think is important. There is a tendency sometimes to say there must be one API that is used for everything, which was done in Vulkan. But when the use cases are so drastically different and so complex in the details of the mapping of one API to the different implementations, the one API restriction may make the solution actively terrible for both cases instead of making it actively good for one. And I think these are the cases where you should have two APIs. One is optimal for this much narrower subset. Like, remember this one subpass thing? It still works well for mobile, as long as your frame structure doesn't have this complex deferred shading like setups. It is still good for mobile. Roblox frame structure is like all like that. Granted, we don't do deferred shading yet, but it can work really well if you structure your frame like this. A lot of other games would also be satisfied. Doom, I think, doesn't use subpass. Doom 2016, I don't think use subpasses. Maybe their newer generations do. I don't know. Doom has more leeway in a sense because they're now Vulkan only, except for consoles, I would imagine, which is much easier because they don't have to worry about like API compatibility and stuff like this. Anyway, so dynamic rendering is awesome. Best thing to happen with Vulkan ever. Makes the API much easier, makes the API much nicer, etc. Doesn't solve deferred shading on Tyler's problem. My claim is the solution we had in place didn't really solve that either, and so we need a new solution. And so I think the question is, what is the new solution? I can't comment, and I don't think I actually know much about that. But Metal has a solution for these problems, which is called image blocks and tile shaders, which effectively more directly exposes to you what you can do on tiling hardware to shaders. Like, you can allocate a resource that looks like a texture, but then it has to fit within the tile, and then you can query the size of the tile, and then you can write and read to this texture and stuff like this. And Metal supports this on all of their mobile hardware, and I guess now M1 chips and M2 chips, but not the desktop class hardware. So this is the case where if you want deferred shading, you have to have two implementations, which sounds bad, but I think it's actually good. Because it forces you to make your mobile-friendly deferred shading implementation to actually be like mobile-friendly, as in you have to think about the restrictions, you have to think about the optimal algorithm design, etc., etc. As a byproduct, you often get a different implementation from a different high-level frame structure that you got on a desktop-friendly deferred shading implementation anyway. So I would claim it's a good thing that you have two implementations. Some people may disagree, which is fine. I do want to say, I don't know. Apple has it easier in the sense that what they've done is essentially this. They said, we have a bunch of desktop GPUs. We are not going to solve this problem for them. They're fine. And we have one type of the GPU that we control, one architecture, that we are going to design an API for that fits it well. And because we control the whole ecosystem, all our future architectures will look sufficiently like that one that we don't have to worry about stuff. So, it's a simpler problem. Vulkan has a more complex problem because it, even on mobile, it targets like 3 to 4 diverse architectures that are substantially different in how the tiler works. So I don't know if the metal solution even works in Vulkan space. But I would claim essentially that we are better off, substantially better off, because now we have dynamic rendering, which you should use basically all the time. The only reason why you shouldn't use it is you are specifically targeting mobile hardware. You specifically designed a simple algorithm that is okay with the restrictions, right? So let's look through this. You have designed the algorithm such that number 3 is not the problem for you. And number 1 is not the problem for you because it's only a small, simple, relatively simple thing with like a few subpasses. Number 5 is not a problem for you because you have validated for that specific simple thing that your specific construction works optimally. You don't care about number 4 because you only use it for like this one case where dynamic rendering doesn't work. And number 2 is still a problem for you, but you deal with this because you really wanted the efficiency gains. So like you still can use obviously subpasses if you really want to, but my claim would be that 95% of Vulkan users can just do dynamic rendering only, like not worry about stuff. Obviously assuming that you're okay with Vulkan 1.3 as the minimum requirement, which right now might be impractical, but it might be practical in a few years. All right. That's all I have to say about dynamic rendering and render passes and subpasses and all of that. Render passes are softly I think render passes are tied to frame buffers, but you can break the link with imageless. But even with imageless, you had to have a frame buffer to specify the size, and it's all complicated and weird. Like, I don't recall which direction the arrows go to. Anyway, I'm really happy all of this stuff is behind us. A render pass is optional. I mean, I assume the render pass and these rendering infrastructure that I was showing are exclusive, but I think you can still create a PSO with the render pass and use it in dynamic rendering context, maybe? I'm not fully sure. I'm so glad to not have to think about the word render pass that I don't actually know. I don't know how they exactly mix together. RTNA 1 supports rendering to 9995. Yay! That is great to hear. That is a very good move. I knew Apple introduced support to this either last year or 2 years ago, I forget, in some new, maybe 2 years ago, in some new generations of GPUs. I was very happy about this, but I think for Apple it's a little bit easier because when you blend, my understanding is they still blend in half precision, and then it's just the final write that they convert from half to 995. And with the immediate mode GPUs, you have to have your blend unit essentially decompress 9995, blend, and then recompress it, because it's unlikely that you can do blending with shared exponents without doing that. But anyway, it's doable. It's just something that required extra circuitry, I would imagine, on everyone's part. But it's great to hear that AMD does this. Really good move. I don't know if NVIDIA still doesn't do it. They really should. 9995 should just be the standard format for anything HDR. The fact that we have spent the last 15 years talking about HDR is the big thing, but the render target format is 64-bit is a little annoying because it's a lot of extra bandwidth, And you can use a smaller format, but then you have to fix a bunch of precision issues with smaller formats, which is just annoying. Oh, hey, validation requires an interpret to be null PTR. Okay, so maybe you have to not use null PTR. Sorry, maybe you have to not use render passes when you use dynamic rendering, which would make sense to me from the specification perspective, because like it's just difficult to specify the interaction. So that would, like, they could technically allow single subpass render passes to be used in context of dynamic rendering, but I could totally see why like this is not a thing. I don't remember this bit because I was just, okay, great, I assume render pass is null when you use it. I don't care what happens when it's not null. All right, so let's look at where we are. Maybe, hold on, I need to... but we are close. The dynamic rendering was the second big topic. I will talk a little bit about some... Oh, God, hold on. So it enabled low power mode, and that forces... Apple. Okay, now hopefully. Okay, all right, that problem is fixed. The question about what's more efficient, metal or Vulkan, is very difficult to have an accurate answer to. Maybe the accurate answer is neither. It depends. It depends a lot on implementations, and it's impossible to compare them directly. The only way to compare, like, because hardware is different, drivers are different, like, you're always comparing apples to oranges, quite literally. The only comparison you can make on the Apple platform is that is, I don't know, like maybe useful, is a Vulkan app running through Molten VK. That's always going to be slower than Metal because you have extra overhead, and Molten VK in particular has an enormous amount of overhead last time I checked. So, but this is not because Metal is faster than Vulkan. It's because Apple doesn't support Vulkan directly. The only way to do this comparison truthfully is if Apple in earnest implemented a first-class Vulkan driver, which is never gonna happen. And so, like, there's theoretical arguments for why one could be better than the other. Usually Vulkan wins these arguments in theory, as in it's usually possible to write a faster driver for Vulkan than it is for Metal, but it is not the useful fact, because the actual useful problem is, given the hardware, what can you do? And you can try to compare like NVIDIA's Metal driver versus NVIDIA's Vulkan driver on Windows, but that's also not a useful comparison because who knows how much time they have spent doing this. So like, I think realistically Apple, and I think Metal is Apple only, and realistically Apple is going very quickly into the world where you always use Apple designed hardware on Apple platforms, and this makes the comparisons completely moot. Because like there's no NVIDIA GPU on an M1 system, so like why do you care about Vulkan if it's a useless sort of piece of information, whether it's fast or not, right? You can still use secondary command buffers with dynamic rendering. The threading questions don't change. Like you still have to. Oh, cool. I didn't actually know this. Yeah, so like you can still, I think, use secondary command buffers. But secondary command buffers are a complex feature. I forgot to talk about this, but it's actually an important point. which is that secondary command buffers are made worse by the fact that subpasses exist. If I remember correctly, there is like complex interactions with all of this. And because of this, there are some drivers on mobile, I forget, are maybe, don't quote me on this, that I think recommend that you don't use secondary command buffers unless you absolutely have to. So yeah, I didn't know that. I forgot dynamic rendering has, if it has suspend resume, assuming the mobile drivers don't flush on that, that is fantastic. That's like at the next level of API simplification. Because if you cannot talk about, I would need to look at the details. I would need to look at the details. But yeah, there's some weirdness with the secondary command buffers on some tilers that is not helping the case of render passes. Let's just double check, because I don't remember this bit. Last time I looked at the actual, this is not the spec, hold on. Last time I looked at the actual spec for dynamic rendering was like a year ago, I think. So yeah. Okay, so you can use them with secondary command buffers. All right. Yeah. Yeah. This effectively means that the tiler doesn't need to flush unless, I wonder what action commands. I guess dispatches are action commands. Okay. Yeah, okay, so this means you effectively don't need, this was another problem in Vulkan where to do rendering on multiple threads you had to use secondary command buffers, or you had to break the render passes in two, but breaking the render passes in two was actively really bad on tilers because you had to like store memory from tile, like you had to break the sequence. With this, in theory, it's possible that tilers can support resume and suspend without the round trip to the main memory. This is the thing that I would ask vendors about, because I could imagine cases that make it more difficult for tilers to, you have to like buffer the render pass. Oh, but you I guess you know that it will be suspended, so you know. Okay, yeah, so this should make it so that you actually don't need secondary render passes, I think. Which is good. But if you do use secondary command buffers. But if you do use secondary command buffers, they still work. You just have to pass a flag. Okay, this is even better. Dynamic rendering is very good, very good. Please use it if you can. Okay, so let's go back to the list of things, and I want to quickly check some boxes on smaller extensions before we talk about the last topic. So we talked about dynamic rendering. I mean, let's just talk about this a little. Let's just go through the list. So copy commands. Copy commands is a very boring extension. It like adds a way. I think it's required. I want to say it's required by synchronization 2 or something like this, but effectively, in Vulkan, there's this general problem that sometimes the commands that exist in Vulkan 1.0 forget to include any way to extend these commands. So if you look at cmd copy buffer2, it has this struct copy buffer info, and the struct has a way to specify an extension struct on top of this. If you look at the command it replaces, it just has 2 arguments for buffers, region count, and the regions, which is just offset and sizes. There is nowhere here to put an extension struct, which is actually very good for API ergonomics, as in it's easier to use this one than this one. But the problem is that when you ship an extension that wants to extend the semantics of copying, you can't use this command. And so there's sometimes in Vulkan cases like this where like this could have been in Vulkan 1.0, but people forgot, and now we have to. But like the equivalent otherwise, it's just it's like a technicality. It's not interesting by itself. So we have talked about this. I don't remember what this is. This is some relatively boring thing, I think. Oh yeah, it's gonna be interesting to. I'm just gonna skip this. I don't want to prolong this too much. This is not like interesting enough to talk about this, I think. It's an important feature. Sorta, kinda. So let's just call it not important enough. It's like important in some very specific circumstances. This is just a collection of small stuff that I assume we will also skip. Let's see. So this is a little nice. I think I wanted to talk about this a little bit. A lot of the stuff is like small technicalities. You'll have to read them and think, do they affect your renderer? This is a little nice because normally the way you create an image object, or I guess a buffer object, is like this. In Vulkan, it's pretty weird. You create the buffer object. Then we probably have, do I have Niagara here? I don't, okay. You create the buffer object, but it's just a dummy handle, like you don't know anything about this. Well, you specify the size and stuff like that, but it doesn't have data associated with it, like you can't use it. Then you ask this buffer object, okay, how much memory do you need and what alignment requirements are there for it and things like that. Then you allocate this memory and then you bind the object to the memory, which is, it can be a little awkward. I forget. I don't think it's a huge deal in practice, but this means it's more difficult to pre-create a lot of stuff. Like, it's minor annoyance, I would say. I forget if there is like actual specific significant problems with this. I want to say no, but it is definitely annoying. And now you can just ask, given a buffer of this structure, how much memory does it need? And then you can separately create and bind it, which could be nice in certain small cases. But everything here, everything in this extension in general is like very small and like not super interesting. So shader integer dot product, you probably don't care. Because it's an extension that is exposing a feature that some GPUs have, where there is a set of instructions in these GPUs to do dot products with small precision, with low precision. Dot product in general, SPIR does have dot product, but for like floating point vectors. But this is useful for example, so some GPUs have support for 8-bit integers and dot products on 8-bit integers. And this is useful for machine learning because there are certain classes of networks that you can make use 8-bit math, and the GPU has a higher throughput of doing this math per component versus alternative options. And so this is nice. There is like a lot of instructions that this adds, or a lot of specific versions of instructions, I should say, that this adds. I guess we can look at this to look at the actual list of instructions. which is smaller, but I think some of this is type dependent. So you can like, some of these bits are, can you have like this instruction and pass a value of this type in? Unless you're doing ML, it's unlikely to be useful to you, because in a random shader, you won't be able realistically to use this because it's not universally supported. So like, whatever. So not a huge deal. This one is also not, it's like valuable, but not super interesting to talk about. This allows you to attach instructions to this PRV shader that any driver can just drop. Previously, we were in an unfortunate situation where you have a set of instructions that can go in a shader, and then you can extend the instruction sequence with new instructions. But every implementation has to support these extensions for the shader to be able to be created, which is generally reasonable. Like, you know, you can't expect something like this to work on a driver that doesn't understand what an integer.product is. But there are certain cases where you just want to attach metadata, like my shader uses compute shader workgroup of a given size, or like my texture input number 2 should be of this format or whatever. And this is an information that you'd expect the application to be able to extract from the shader from the shader PRV bytecode, but not the driver has no use for this information. And so this is just a way that you can attach this information directly to the shader bytecode, which is like convenient for tooling interactions. It's a good idea. It's just not, it unlocks new possibilities for tools. It doesn't really unlock new possibilities for applications, because a specific application could always funnel this information like outside of the shader bytecode. So we already talked about this. Oh, I wanted to talk about this in concert with this for some. They're not really related. So we'll talk about synchronization at the end. This is super trivial. If you have a compute shader, it can have what's called local storage. It's called workgroup memory in Vulkan, I guess. It's called local storage, thread local storage, something local storage. In Direct3D, it's probably called something else in Metal. It's like a way to associate some memory with your compute shader that persists, that is shared between different threads in the compute shader within a workgroup. There's this general problem in Vulkan, which is that when Vulkan was specified, there were a few cases where certain behavior in Vulkan would be undefined, which is great for performance because this means implementation can do whatever. But it's bad for security because, for example, if you forget to initialize workgroup memory, if you explicitly don't initialize workgroup memory, let's put it like this, and then you read from it, what can happen is that you are reading data that was left by a previously running compute shader. And you would think it's fine, and it's probably fine if it's all in context of one application. But if you are running this in context of a web browser, maybe the previous compute shader was dispatched from like a different tab that wrote some data, some like image data into this memory that was actually pretty sensitive. And now you can have a compute shader that like reads it directly. So this is an extension that is, I think, primarily useful for this, where you can just enable a bit when compiling all compute shaders that will clear out the workgroup memory. And on some GPUs, this is more efficient than explicitly clearing this by patching the shader to like zero it out, you know, by hand. So this is that. This just adds some fixed point formats that are 4-bit. 4 bits like this. So this is 16-bit, 4-bit per component, and it's an integer, not an integer, sorry, it's like floating point 0 to 1 normalized. So you get between 0, you get 0, then 1 divided by 15, then 2 divided by 15, etc., up to 1. 4 bits doesn't seem like a lot, but it sometimes is enough. And of course, if you have an application that was using this format in context of Direct3D, then you kind of want this format to exist. And the fact that one of the contributors is from Valve suggests that this is probably important for Steam Linux translation ecosystem, and specifically Steam Deck. So that's my guess, but I don't know. It's a logical conclusion that I would derive. All right, so this takes care of this. So this is sort of also somewhere between the portability extension and security extension, because Vulkan has a mode where it's called buffer robustness, I think, or just robustness, robust buffer access, something like that, where it says out-of-bounds buffer accesses have predictable, consistent behavior, but it didn't have this for images. Direct3D actually specifies this for images. The problem is there's no... Oof. Some parts of the spec are difficult to navigate because of this, okay. So Vulkan didn't have this feature existing for images. And so the behavior for image access outside of the image bounds from like compute shaders or something like this, not when you sample the texture, but when you read from an image or write to an image, it would be undefined. The reason why this is a problem is that when you're compiling an application that was built for Direct3D 11, it may accidentally or intentionally do out-of-bounds image accesses that have a very predictable behavior. And because Vulkan... All right, small blip again, but it feels like we are back. So to replace this behavior, so Direct3D defines this, Vulkan did not define this. To actually build an application that defines this in Vulkan, you have to have every shader check every single image load store against the image bounds and emulate the guarantee that Direct3D provides. That's a pain. That's a performance problem. And some hardware can provide this guarantee for free because some hardware was built with an assumption that it needs to target Direct3D 11 where this guarantee is provided. And so this allows you to access this guarantee. Just like with robust buffer access, both of these are like, unless you have to rely on them, you probably shouldn't rely on them because they may actually slow things down. But if you have to rely on them, then it's better to rely on them through the API as opposed to having to emulate this. So this is mostly important for that portability story for Steam Deck again, but the other side of this is also if you are running in a browser where you want security guarantees, it would be a problem if your browser exposes compute shaders via like WebGL or WebGPU. And in these compute shaders, you don't give guarantees that are very strict about what happens to out-of-bounds access, right? So a lot of these come together. Like the Direct3D 11 had a very good security story around this class of problems. And because of this, it's both the case that there are applications that care about strict compatibility with Direct3D 11 and applications that care about security and so want similar guarantees. And so Vulkan ends up providing some of these through extensions. So that's all I have to say about this. My list only has 4 extensions to go, including synchronization. Ext tooling info, which we skipped, is not particularly interesting. The idea there is when you run Vulkan, Vulkan has these mechanisms to inject code into your application that are called layers. And these are often validation layers if you're developing your application, but they can also be random layers made by random people who randomly install them on the system that the application is running on. Steam has a layer which it uses to display the Steam overlay on top of your game rendered content. Any video recording application may have a layer that it uses to both capture the output of your application, but also inject some extra overlays. Various programs like Reshade or whatever could inject a layer and do whatever. And what sometimes happens is you get bug reports from users like, oh, like your game doesn't render correctly. And actually the problem is you have a layer loaded that breaks the game. Or you get crashes via an automated crash reporting system. And they only happen for people with a specific layer installed, but how do you know that? So this is just a way for applications to automatically collect the layer information and like some other stuff, so that you can report it with bug reports, with crash reports, etc. So that instead of trying to figure out if you have something enabled, you just know, is it enabled, is it not enabled? So it's like mostly relevant in the context of desktop with people installing random stuff. Okay, 3 to go. So let me switch to this. So we have 3 things left to discuss: synchronization 2, inline uniform block, and subgroup size control. Let me look at the chat. So I don't currently have plans to continue Niagara series. 1.3 specifically is not hyper interesting in context of Niagara. Niagara has very intentionally like 2 render passes, something I forget. You can use some of this stuff, you can use some of the 1.2 stuff in context of Niagara. I don't know if I want to yet. I wanted to, there's like some interesting stuff that, oh shit, I can't talk about this. Maybe some things will happen there. I don't, like there's some things I wanted to do, but like I don't know, it's a little complex for ambiguous reasons. So I don't know, we will see. One thing I was thinking of today actually is, one thing that could be fun is to do a Niagara port to Metal, which I think I might actually do because it sounds fun. And it's like a new spin that I don't. The reason why I did Niagara is Vulkan is a difficult API to get into, and a lot of the tutorials are very basic or way too like I didn't like how they approach the introduction sequence, and I also wanted to experiment with some newer features, including some rendering algorithms for occlusion culling and mesh shaders and indirect dispatch and all of this. For people who don't know, Apple announced Metal 3.0 that has mesh shaders, which is one of the features that Niagara uses. And so I was thinking actually it could be interesting. I looked briefly at the mesh shaders in Metal. They are very similar to mesh shaders that NVIDIA provides via Vulkan extension. And that is now a Direct3D12 feature, an optional Direct3D12 feature. So I was thinking that could be interesting, both because it's a very different API, and also because it could be a good introduction to, again, Metal from scratch, right? So like similar way how we did Vulkan. People are probably less interested in Metal by and large than they are in Vulkan, but I think Metal is a great API that is just like very pleasant to talk about and use, and so it could be interesting to do this more complex example from scratch. And it's also an opportunity to figure out mesh shaders in Metal. How do they work? Do they work well? Are they performant? stuff like that, right? How portable is it? Like, can I take something that was built for NVIDIA mesh shaders and just port it to metal mesh shaders without too many issues? Does it work fine? Does it perform fine? So I think this is something that I might do. No promises. It would require, I don't think it's the same scale as Niagara series, because Niagara was like 14 streams or something that are 2 hours each, so that's like a lot of time. Metal is probably going to be way quicker, and I have the code written, so it's just a porting exercise, right? But at the same time, it's still a bunch of time. And I do have a MacBook. It has an M1 chip, which I haven't checked if mesh shaders support M1 or if it's M2 only, but I assume M1. I would need to figure out, my video streaming setup is Windows specific, right? Like I never streamed from Mac, so like I need to figure stuff out. But this is semi-likely to happen, we will see. But for Vulkan, I don't have anything planned right now. 1.3 specifically is not interesting enough to maybe I could dedicate one stream to like just porting stuff to dynamic rendering and things like this, but it's not like a huge deal. So not super likely, I would say. All right, so let us cover the remaining three. We'll talk about synchronization last because it's a bigger update. So we have subgroup size control and inline uniform block. Oh, Molten VK. Yeah, the problem with Molten VK is, so like Molten VK won't support, I mean, I assume Molten VK doesn't have plans to support mesh shader translation from like NVIDIA extension to metal. If they do, it could be interesting, but mesh shaders for metal are new as of like, what is it, last month? 2 months ago. I forget when WWDC happened. You can run Niagara without mesh shaders, and so you can attempt to run Niagara via Molten VK. The caveat is this. So I talked about Molten VK performance problems, right? They are all on the CPU side from what I know. As in, the reason why I know about them is I actually tried to port a rather significant application, which is the Roblox renderer. Now, granted, this happened a few years ago, so like maybe things have changed drastically there, but the outcome there was like it worked, but the CPU cost, the CPU overhead for the translation was significant. And the reason I know this is because we support metal natively, and so like you could do an apples to apples comparison, sort of. The Niagara renderer is structured such that there is like no CPU work that happens, right? Everything happens on the GPU. The draw dispatch, the calling, the submission, like it's all on the GPU. So with Molten VK, the question is like, will it work? Maybe it will, maybe it won't, maybe we'll find bugs in Molten VK, but like it's not, you know. So it's a little interesting, but the bigger reason why I'm interested in Niagara on metal is it's an excuse to just like dive into mesh shaders on metal and just like look at how comparable they are to what NVIDIA has. If mesh shaders didn't exist on metal, I would not really be thinking about Niagara on metal, I guess. So I think this is the question. The indirect dispatch, I guess, is maybe there is still a reason. So anyway, yeah, I don't think Molten VK would be super interesting to do for me personally, but yeah, like a metal port could be interesting. Anyway, all right, let's finish this. It's been like 3 hours. But we should get through this in a reasonable amount of time. When I did the WoW stream 3 weeks ago, I was super tired at the end, even though that was just a couple hours. But today, A, we took a break. B, I guess you just gain stamina for streaming. So I'm not actually very tired, which is good. Okay, so subgroup size control. It requires a little bit of exposition, but not a whole lot. I will omit most of the critical details. Who did this, by the way? A lot of people from all over the place. So here's the short story. Vulkan 1.1 introduced the notion of subgroups, which if you haven't seen, I forget if I talked about them at any point on any of my streams. We tried definitely to use them in Niagara for some atomic thing. And then I think concluded that the driver does the same optimization perfectly, which is often the story of subgroups. But the short story with subgroups goes like this. So I just talked about quads, where GPUs process all fragments in quads. Actually, the GPUs don't process all fragments in quads. Actually, GPUs group the quads into a superstructure that Vulkan calls subgroup, even though it's superstructure. But I guess it's in relation to work group, it's a subgroup. So the GPUs tend to process anything in units that range between optimistic, let's just say 4, but 4 is rare. Realistically, so Intel has this thing where it's like 4, 8, 16, I want to say, but really NVIDIA processes things in units called warps that are 32, and in more recent, as of like 10 years ago, they have this half warp structure, which sometimes things work in half warps, sometimes things work in warps. But like 32 is the magic number. AMD used to have the magic number be 64, and then with, I want to say RDNA 2, question mark. I think in the RDNA 2, they have like this hybrid structure, which is like 32-64. So it's like kind of 32, but it can kind of do 64. The numbers for all of this, they refer to the fact that whenever the GPU works on like a pixel in a fragment shader or on a compute thread, it actually works on, for example, 32 of them at once. And it does roughly the same, details get complicated around NVIDIA, which I'm not even an expert to discuss. It's a little intricate there, as I understand it. But the simple mental model is, I think, I want to say MJP, had a great blog post about this from like a couple of years ago, about a like fake GPU. There's like interesting details about how branching works. If you have 32 threads that have to do the same thing, what happens is one of them takes a condition. And we kind of talked about this when we talked about discard, like what happens is if one fragment just disappears. Anyway, but the simple mental model is you have a shader, there's no branches, and actually there's 32 copies of the shader running, 32 threads running at the same time. They do the exact same thing in lockstep on different data. Which raises the question, can I, a thread, ask 31 other threads about the data that they have computed? We talked about this when we talked about the finite derivatives, and so when you do ddxt, what actually happens is that the other fragment that is next to your fragment has computed their own version of t, and so you can take your t and their t and subtract them. Well, actually there is 32 of those, not like 2 or 4, so can you ask everybody else what their value of t is? And so the answer is sorta. There is the concept called subgroup, and there's subgroup operations, and we are not going to talk about all of this today because, you know, it's like a long topic. But there is some limited amount of operations that Vulkan exposes, and Direct3D 12 exposes. Direct3D 12 calls them wave operations, wave ops. So you can use them. The fun thing is that Vulkan tries to define things such that it's all doesn't depend on the actual subgroup size, but the actual subgroup size may matter. It may matter for specific algorithms. Some specific algorithms may be designed to work only for a specific version of only for the specific subgroup size, like 64. And Vulkan has a way to tell you from 1.1 what the subgroup size is, but it's one number. It turns out that, for example, on RDNA2, it's not one number, it's like sort of two numbers. And on Intel, it's sort of three numbers, and they can differ per shader. And so the actual hardware, turns out, is more complicated than just a single width of the subgroup or whatever. And so because of this, this extension allows the implementation to say, instead of saying my subgroup size is 32, it would say, well, my subgroup size is between 32 and 64. And there is also a way to ask the shader to be created with a specific size, which will fail if the size is not supported by the hardware, but will succeed otherwise. So you could, for example, have, when you have a console game, you basically assume that it's GCN, and GCN is basically 64, because I guess I don't know how the recent consoles work, but whatever. And so you assume 64, and you have shaders that were written assuming 64. What you can do when porting this to Vulkan now is you can have two versions of the shader. One doesn't even use any of the subgroup stuff, and one only uses 64. And you try to create the one that uses 64, and then if it fails, you just fall back to some other implementation, which is like, you know, it's a possible way to optimize. If you have a specific expectation about the target hardware. And there's some other small things around this. For all of this, the situation is, if you already use subgroup ops, then you're probably interested in this extension, you probably understand why it would be useful, and you might be able to apply it. If you don't use subgroup ops, then this extension shouldn't motivate you to start using subgroup ops. It's just extra control over a feature that's already complex and like specific to begin with, let's put it this way. So that's that. All right, inline uniform block, and then we will finish with synchronization. So inline uniform block. I am not a huge fan of this extension, but I know why this exists, so we can talk about this. The reason why I'm not a huge fan is there is this tension in Vulkan, which we already talked about in context of render passes, between specificity and genericity. Do you expose many different versions of a similar concept, because there is a big mismatch between them in terms of what the hardware supports, and so you want to give applications the optimal way to give a given thing, or do you expose a single generic way to do this? When Vulkan was designed, was a question, how do you pass data to shaders? And how do you pass resources to shaders? And the answer was, there is two ways to do this. There's one way to pass data to the shaders is to pass it via resource objects. And so to pass an object, you use descriptor sets. So you pass a descriptor to the object in the descriptor set, and then inside the shader you get the object, and then like load data from it, right? So this is how uniform buffers work, how textures work, how image objects work, how like everything works. And push constants. The idea with push constants is it's a very small amount of data that you can pass directly to the shader stage. It is optimal from the CPU perspective if there's very little data there, because you just write this data to the command buffer and you're done. It's like writing, I don't know, if you have to pass 12 bytes, the hope is the function call to set this data just copies 12 bytes to the command buffer and like you're done. It's more complex, but like the hope is there. And on the GPU side, there is no indirection, because each shader stage gets access to this single small constant block, and it can read data from it. And when there's a lot of data, you would use descriptor sets, and then what happens on the GPU is you have to load the data from the buffer. The problem is, and then since then we got two new things. One is push descriptors, which I advocated for at some point on Niagara streams, and we used it on Niagara, but the problem with push descriptors is it's a KHR feature that is not consistently supported on all the drivers, and I don't think there is a future where a Vulkan version mandates support for this. So, like, maybe it's a dead feature at this point, because you can use it and some drivers support it, and for some drivers that support it, it's faster to use push descriptors in certain scenarios than descriptor sets, but like... and then the second feature is this new thing called inline uniform block, which was an extension before and now it's part of 1.3. I'm assuming it's optional. Let's see if there is a require. This makes me think it is optional to support it. Let's see. But I could be wrong. Okay, we need to go here. It is indeed optional from what I can tell. So what this does, why is this useful? And then why do I not like it? Why is this useful? So let's say you want to pass data to the shader. Let's say it's a reasonable amount of data, but it's not like an overwhelming amount of data. Push constants have an API minimum limit of 128 bytes, I think. Like any hardware, any driver has to support push constants up to 128 bytes. But the actual reality is that on some hardware, the efficient limit is smaller, much smaller. As in, if you go over some limit that you can't access, that you can't ask the API for, then you go down the slower path for push constants, which increases your submission cost. When I talk to people about push constants specifically, my recommendations tend to hover around, like, I don't know, 16 bytes is a good number. If you can fit the data in push constants in 16 bytes, you should probably use push constants. If you go over it, it gets complicated. If you go much more, like 64 bytes is already unreasonably large, 20 bytes may be okay, even 16 bytes might be borderline on some hardware, it's like difficult. An example I used in the Vulkan optimization article that I wrote for GPU Zen was 12 bytes, I want to say. 12 is a good number, so this is like the ballpark. Okay, what happens if you actually want to pass more data, like a kilobyte or something? 512 bytes, I don't know, not like a megabyte of data, but not like 16 bytes. Well, you have to use uniform buffers. The benefit of uniform buffers is you copy the data on the CPU, then you can use it. You can use it in multiple draw calls, it's easy. The downside of uniform buffers, especially for especially for small amounts of data, I guess, but just in general, goes like this. The way some implementations implement uniform buffers without naming names is like this. You have a descriptor of the buffer which contains pointer, size, I guess there's not much else to say about this. There's a pointer and size. I feel like I'm forgetting something important. Whatever, let's just say it's pointer and size. And then there's the actual data, right, that you like have to reference a pointer to get. But the way you get the descriptor in the shader is by loading the descriptor. So this is let's call it 16 bytes for simplicity, because 8-byte pointers size, you have to align the whole thing. Like, let's call it 16 bytes. You may be able to fit the descriptor in some very small bit of memory that corresponds to, that's like a modal equivalent of push constants, I guess, but maybe you can't. So a very common layout that you may see on some specific GPUs in practice is like this. The shader gets a pointer to a descriptor set. Hold on, I need to. So then the shader can dereference this pointer, which looks like a bunch of descriptor objects. So the shader can read the descriptor object from that pointer, and then using the pointer in that descriptor object, it can read the actual data. You will note, and the second, the only thing that the descriptor set stores is the descriptors. You will note that there's two indirections here. Two indirections are bad, or they're like maybe okay, but like it's worse than one. And so what you might want to be able to do is to store the actual data like here, so that instead of reading it via two indirections, you only have to have one indirection. And because this thing corresponds to a descriptor set object, what effectively you want to be able to do is to store the constant data, like the floating point values, inside the descriptor set. The benefits is that it's just memory. So you can store more data there. You don't have these arbitrary, very tiny limitations of like efficient push constants. And once you put this data there, you can efficiently access it. And you don't have to upload it more than once, because, for example, maybe what you have is you have a renderer. I guess I don't dislike this feature. I just separate conversation. But so like there is some straightforward mappings from a higher level renderer to this feature. For example, a lot of people obviously in their engines have material systems. And what is a material? A material is a bunch of resources and a bunch of constants. And it is pretty straightforward, usually in some systems like this, to map a material to a descriptor set. You map every resource to a descriptor, then when you load the material from file or whatever, you like create a descriptor set object, and then you're done. You can just use it. You don't have to upload the descriptors every frame. The problem is that you have to put the constants into a buffer, which has this two interaction problem. And so if you have space within the descriptor set for constants that you can just put there, then it's nice because you can just like put them there. You save it in direction on GPU, it's a little bit faster. It maps a little bit better to what some people do in the console world. I have this general hope. So like it's fine. Not all hardware supports this. From what I from the description, I guess, from the extension description. This makes the use of this a little bit questionable in practice. Oh, I think this is a feature in Direct3D 12 as well, but maybe it wasn't there from the beginning, I forget. If you can't rely on this feature being present, the question of whether you want to use it gets a little bit ambiguous, because I think you have to change the shader code to be able to use this feature. So can you actually rely on this? Like, there are some questions around this. But it does improve performance in certain cases, which is good. The reason why I don't love this is that I feel like, to me, there is a very obvious destination where everything will converge. And this destination is bindless renders. I think while we still talk about descriptor sets, we talk about descriptor sets out of necessity, as in some hardware supports them as the most efficient way to do this. Some hardware doesn't support bindless or isn't efficient at bindless, so you have to design a renderer for the lowest common denominator, etc. But to me, there's only really one future, which is bindless. There's like problems on the way, there's problems with tooling, there's some hardware support questions, but to me the only real future is bindless. To me the only real future is that the descriptor set object just like dies completely, or it exists. I mean, realistically it should just disappear. Like, to me the real future is you like you get pointers into the GPU data, you access everything through pointers. Whenever you have to solve these problems, like you want to have a single pointer that you can read floating point data from, you still solve these problems. But the way you solve these problems is that you declare this descriptor set as a structure that has a layout that you control, and part of the structure is descriptors like these guys, and part of the structure is constants. And these descriptors are actually like indices, and then when you have to sample like a texture, you have an interaction. Like there's things to figure out, but while we have an API that implicitly creates this layout that the GPU can understand, I think we haven't won. I think we have only won when, from the GPU perspective, it's all just like data. It's all just bytes and like pointers to handles, or like handles to resources, sorry. And your entire interaction goes through that. And so my expectation is that in like, I don't know, a decade, there is some new API, or maybe it's like Vulkan 4.0, or maybe it's some API that has a new name. I don't know what's a good name after Vulkan, where the only thing that's in the API is the bindless style access to resources. And we just forget the fact that descriptor sets exist. And so whenever I see like, oh, hey, here's like a new way to specify data to the GPU through the descriptor sets, I kind of get a little bit sad, because to me this is a little bit it's like we are still in the present instead of trying to be in the future. That said, being in the present is important, and there is like an important performance question to be asked here. So fine, like if people want to use this feature, it's cool. I'm just not personally very excited about this because I don't think it's the future. So if they're required, this is a little bit of a different story, but there is this, I don't see why they would have a boolean in the device properties that say whether it's supported if it was required. So I'm, let me look at the reference that you have left. 41.1 feature requirements. This is interesting. So if it's required, it's better because at least you can rely on it, right? So like at least you can just architect your renderer around this and you're gonna be fine. Why is it because of the weird like extension core promotion? Right. This thing relates to the ext extension. It doesn't relate to the promoted version of this extension. Right, and the thing you do have is the max inline uniform total size. Let's look at this limit, by the way, because that's another thing that's important. Like, can you design a renderer so you can rely on the feature? What is the limit requirement? Right, there's 2 limits per pipeline, and okay, where is the requirement for this limit? It must be in 41. Must be here. Wait, no. Hold on. No, yeah, okay, we're here. $256 bytes. Okay. Is the push constant limit 256 or 128? I forget. I felt like it was 128. 128. But it could be that. Okay. 256 bytes. Yeah, it's borderline. If it was like a kilobyte, it would be comfortable. 256 bytes is a little bit borderline. It's a little bit borderline. It's like, okay, you have to pack stuff pretty aggressively within your material implementation though. Because if you don't pack it, you're gonna run out like pretty quickly. Because if you don't pack, you will have, I don't know, what is it, like 16 colors with alpha? It's not a whole lot. Yeah, I don't know how I feel about this. If the limit was a little bit higher and it was required, then I would see you make your material system, like you design your material system around this. Anyway, fundamentally this is what it's for. Yeah, so like it's fine, but I hope at some point we just sort of, like I hope that at some point we start viewing anything around descriptors through the lens of, there's the long-term future where the only model is the bindless model. Okay. How can we make the bindless model usable, performant, user-friendly, yada yada? How can we move there and everything that isn't on that path, we just don't spend time on, right? So, but whatever. I mean, again, like on consoles, inline uniform buffers or equivalents are often used by production renderers from what I know, so I'm not surprised. There is a certain aspect of API practicality where there's certain features that are important in the now and maybe less important in 10 years or unimportant in 10 years, but important in the now prevails, which I'm cool with. It's okay. All right, the final thing that we need to talk about is the synchronization to API, which is gonna be hopefully reasonably short and sweet because it's a difficult topic, but but many of the changes are cosmetic, so maybe it's okay. Yeah, K-share dynamic rendering support, this is actually an important question. So it is required to support in 1.3. It is not required to support in earlier versions of the Vulkan. So when I was saying, hey, you know, only use K-share dynamic rendering, there is a big caveat about this, which is, can you rely on Vulkan 1.3 as your minimum spec? Well, the answer today is no. It's very simple, right? Like, I think it's not practical to require Vulkan 1.3 as the minimum bar today. But this kind of underlies many of the, like, there's always going to be this problem where if there is an important problem that a newer version of the API fixes, can you design a renderer around that or not? And it's always going to be a problem. Roblox heavily relies on Vulkan on Android. We support 1.0. And we support 1.2. Like, we support some of the future levels as an optional code path, but the baseline is 1.0. If we were to require 1.1 today on Android, it would drastically shrink the user base that can use Vulkan. So it's not an option. Obviously, using 1.2, 1.3 is not an option either. If you're shipping a desktop game with Vulkan that requires up-to-date up-to-date Windows drivers, today, then I probably wouldn't recommend it. But if you're shipping this game in 2 years, then maybe that's okay. If you are targeting something like Linux platforms, like Linux itself, or maybe Stadia or something like. I don't know what the situation is on Stadia, but like if you're targeting something like this, then your threshold might be different. If Steam Deck supports native games, like Linux games, then you're targeting a fixed hardware platform, and so from this perspective, your calculus is different. So like, yeah, I'm not saying, oh, people should just switch to dynamic rendering starting today and drop everything below this. But dynamic rendering is not a GPU feature, it's a driver feature. It is important. Any Vulkan implementation that doesn't support dynamic rendering, that is up to date, as in a driver comes out tomorrow and it does not support dynamic rendering. In every case like this, the reason is not that the GPU that the driver supports can't support it. It is the driver developers haven't had the time to support that extension. Similarly, I don't know what the 1.3... Kronos sometimes makes the statements. Let's see. Yeah. So this is an important statement. It says any hardware that has an actively supported 1.2 implementation should be capable of supporting 1.3. So again, there shouldn't be hardware reasons for why something that has a 1.2 driver gets a 1.3 driver. But the problem is real. So like what I'm saying is, on one hand, there should not be adoption blockers to this feature. On the other hand, given the current market, it's probably unrealistic to switch to this as your only mode of operation for a production project. For something like Niagara or whatever, or for tutorials, like not a big deal, right? For a production Vulkan game running on Android, not happening. For a production running game running on Windows, depends, who knows, I'm not sure. For a production game running on Steam Deck, I don't see why not. So it depends. The calculus is different in every case. But I'm hoping that in 3 years, when we have this conversation, I'm going to be like, yeah, actually, you might as well assume 1.3. It is, of course, I would have preferred if dynamic rendering happened in 1.0, 1.1. But I think it took everybody collectively a lot of time to understand, is the render pass model viable as the only model, or is it not? And I think the conclusion is, it is, as I was saying, it's not the optimum, and it is not the only model that that can work, that should work, etc. So, but yeah, like I'm not saying, okay, just switch to it. But it's important that it's a driver problem, it's not really a GPU problem. So it shouldn't be a problem in the future, assuming up-to-date drivers. Do you want to support non-up-to-date drivers? You have to make this decision case by case. All right, so, okay. All right, I really have to finish this in 20 minutes. So let's very briefly, very quickly talk about synchronization 2 for 15 minutes, and then we will end this. Synchronization is a very difficult topic, but I'm going to gloss over most of this. So, hold on, let me go back. Because yeah, I'm also running out of time that I budgeted for this. So, okay. Let me open. There's a couple things I want to briefly talk about this, but it's difficult to. I don't want to spend the time to re-explain synchronization from ground zero, but it's a little bit important. How do I do this? There was a blog post. This is about 2. I wanted. People used to draw these diagrams that were cool. All right, I'm not going to be able to find this. So here's the short story. Here's the very short story. So there is a new extension called synchronization 2. This is a new API to talk about synchronization in Vulkan. Oh, by the way, dynamic rendering, there's one more thing which it simplifies, which is that in Vulkan, before dynamic rendering, there's 2 ways to talk about synchronization between render passes. One is with external synchronization barriers, like an image barrier or something. And the other one is by embedding the synchronization information into the render pass definition. And this is also a source of complexity, because you would think just one is enough, but render passes require you to use sometimes to use the synchronization specification inside the render pass. So you can't like not use it, and you would think that you can just use that as the only way, but there's some drivers that have bugs around this, and it's like complicated. So dynamic rendering, I think, kills that as well, if I remember correct, for the most part. Like I don't think there's a better specification inside the render pass, inside the dynamic rendering info now. So a lot of stuff gets easier. So anyway, so synchronization. There is an API for synchronization starting from Vulkan 1.0 that you have to use if your program is supposed to be correct. The API has 2 issues broadly. One, okay. So one set of issues is the API is sometimes a little bit difficult to understand, or a lot difficult to understand. The topic is complicated. And the other issue is that sometimes the API doesn't specify enough information to the implementation to function well. And so the two example is supposed to fix both, or the two synchronization 2 is supposed to fix both of these, but a little bit similarly to the dynamic rendering, it doesn't. It's not like a huge shift from what we had. It is an API that is nicer to use once you maybe wrap it a little bit, but it's like a little bit cleaner conceptually. It is an API that solves one important case where you just didn't pass enough information to the driver, and the other case is also kind of important, but maybe a little bit less so. But fundamentally, it's a similar model. So fundamentally, you have to understand the Vulkan synchronization model to be able to understand synchronization 2, and I will not go over this. I will just highlight the differences. But once you do understand the old model, understanding synchronization 2 isn't a big leap. It is not a big new concept. It is very, very, very similar. It's just different in details. So let's talk about a couple of problems that the API revision solves. So one is that trips a lot of people up, which is this. So in Vulkan 1.0, when you specify synchronization barrier, there is these 2 bits of information. One bit of information is the access mask, which is what happened to the resource previously and what will happen to the resource now. So in this case, we are saying, oh, before the barrier, the shader was writing to the buffer. And after the barrier, a shader will be reading from the buffer. And then a separate piece of information is the stage. It's actually a stage mask. I can't cover this in 15 minutes so that people who don't understand synchronization start to understand it, unfortunately. So in a very simplified fashion, there's a stage mask because you might want to specify multiple stages here, which again says what happened to the resource before and what happened to it after. So here it said before the barrier, a compute shader was writing to the resource. After the barrier, a compute shader will be reading from the resource. But maybe if you want to do a compute to fragment shader barrier, this is going to be different. You will note that these are in 2 different places. One is in a structure and one is in a function call. That's actually a big deal because this function allows you to specify multiple barriers, and every barrier has its own resource and access mask, source and destination, but they all have to share the stage. So it's in general confusing when reading. It's also especially confusing when you want to have multiple barriers in one function call, because what is the set of stages here? You have to union these. It gets very difficult to think about this, and it gets more difficult to group barriers together, because you can't simply say, oh, there's the structure that describes a barrier. I will just pass 2 of those to a function. You have to think about this other stage information. So in the new API, which I think has, the cool thing about this is that you can literally, there's the 2 pages on the Vulkan website, before and after, and you can flip between them and you can see, okay, oh, I see this is the difference. So in the new API, inside a single structure, you have both the stage and the access mask, and this is much easier to read and understand. And it also fixes this problem, which is when you have 2 barriers, like what exactly do you specify? One minor thing that happened, which was neat, is that because it's a mask, it is not an enum, it is a bit mask. They ran out of stages in the 32-bit enum. There's literally now more than 32 stages that you can specify here, which is ironic, or like it's a sad problem in a sense. But let's see if so as you can see, it was a 32-bit thing and things went well, and then at some point something happened. Oh, maybe we aren't over this yet, but we are too close to the end. Is that what happened? So this is a suspiciously high bit, but there is still like 7, I guess, after it. So maybe it's not quite that we ran out, but there is a sneaking suspicion that the number of bits will end, right? 32 is not enough. So all of these are 64 now. But whatever, this is not like actually important because you don't count these. So the one thing that happened that's important is you specify these together. This makes batching easier and stuff like that. The second thing that is important is that some enums now got grouped. One thing that was really painful, which this highlights, is whenever you would transition color versus depth images, you would always have to specify different masks. Kronos probably has an example on this. If I look for color here, you will have to say, I was writing color to this image, and like the layout that it was on was optimal for color attachment. But an image is either color or depth. And so this information is a little bit redundant, and you would often get it wrong. And when you would get it wrong, sometimes validation layers would complain, so whatever. So this is a little bit simpler. Let's see if I can find the same example. Graphics to compute. So now the layout, it used to say color attachment optimal, now just say attachment optimal, because it didn't really matter. Like you just say I want, like you didn't have to be that precise because the information could be inferred from other places anyway. And the important bit that I want to highlight, which I think this talks about as well. Yeah, so the important thing, and then everything else I will just skip because we're running out of time. Everything else I think is not hugely important. There's some extensibility stuff. All of this is like not very interesting. Like this is the important part about this. That is going to be difficult for for applications to take advantage of unless they use a render graph. Although depends, but it's important. So fundamentally, let's look at the barrier. Hold on, the compute to compute. This is probably the simplest barrier that you can use in Vulkan 1.0, and we can look at the 1.3 version of this because they are like the same semantically. So you meet a barrier. The barrier says there is a resource which is specified in this struct somewhere, or actually this is maybe a global barrier. It doesn't matter. There is a resource that was there is a resource that was being written to from a compute shader, and a different compute shader will read from the same resource. And unless you have a barrier, what can happen is that the writes from the first shader are still happening, or maybe the first shader is still running once you start the second shader. And so the second shader is going to read data that hasn't been fully written to by the first shader yet, and that's a problem. Because contrary to what people might believe, when you have two dispatches one after another in Vulkan, they can overlap in terms of the execution. And so what you have to do is you have to insert a barrier. So let's look at this. Let's draw this. And again, I don't have time to like fully explain the synchronization models, so some of this may be difficult to understand, but you know, such is life. So you have this one dispatch that writes to a resource. And then you have the second dispatch that reads from the resource. And in Vulkan, if you don't have a barrier between them that says that the first one has written to and the second one will be reading it, then you actually have a synchronization problem that can actually result in the second dispatch not reading correct data. Or maybe your GPU dies, who knows. So there has to be a barrier here. It's absolutely critical for the correctness of the execution. However, the way that the barriers are specified by default is you say, I have a barrier, this resource transitions from A to B. The problem is that what often happens in the implementation of this barrier is that we wait for all compute work to finish, and then we start the compute work that has to happen after it. The reason why this is a problem is that the GPU is a highly parallel device, and you're inserting a synchronization point for this highly parallel device that doesn't give enough time for the GPU to process anything else. The canonical example, I think, sort of goes like this. What if you have 2 more dispatches? And actually what happens is, where's my eraser? Don't know where my eraser is. Hold on. Okay. So you have 2 dispatches and you have 2 resources, and it goes like this. Right? So you have a sequence of dispatches. It's probably more than 2, and they are paired. So you have a dispatch that writes to the resource, and then a dispatch after it will read from a resource. But they are spread around in time like this, and the resources are all unique. This is super common, happens all the time in various rendering algorithms. Okay, it could even be the same resources but different parts of the same resource. What happens when you insert this barrier, usually in implementations, is that the barrier waits for all of the work before it to finish fully, and then the work after it starts. This results in serialization that reduces what's called occupancy, usually, like the amount of work or utilization, maybe is a better phrase here, the amount of work that is concurrently happening on the GPU. Usually, if there is more than 2, imagine there's like 100 things before and 100 things after. If you look at the utilization graph of the GPU, where the top is like 100% of possible work that the GPU can be doing, what usually happens is like this. You have it hovering over like ideally 100% or whatever, like some high number. Then it goes down to 0. And then it starts up from 0 and then catches up to 100 and then goes. And the reason why is because there is a barrier here, and no work after the barrier can start until the work before the barrier finishes. So this is a problem because you're losing time, because you could actually be starting work on earlier elements that you probably have already finished, but you don't. The issue is that you're telling the driver, I'm done with this resource, but like it's like not enough information for the driver, and because of this usually happens. You would think that you can, so I said there's 100 resources here. You would think that you can insert 100 barriers, and so here you can insert the barrier for resources number 1. And then you dispatch the thing that reads it, and then insert a barrier for number 2, etc. And you would think that this gives the driver sufficient information so that because the resource number 1 is already finished being written to when the barrier is there, the driver inserts information, the instruction only waits for that specific thing. But that actually doesn't work in Vulkan model at all. And so if you actually do 100 barriers here between every dispatch in the second phase, it's going to be really bad because your utilization graph will look like this, and it's going to be completely catastrophic to your performance. So Vulkan 1.0, 1.1 or whatever, 1.0 probably, maybe not, has this thing called split barriers. Which is, instead of having the barrier as one command, you have two commands: set plus wait. The idea is once you are done writing to a resource, you set a barrier, and once you want to start reading to it, you wait for it. But these 2 points are spaced out in time. And so in this example, after every dispatch in the first group, you set a unique barrier. And then before every read in the second phase, you wait. And the idea, and you have to use like an event object for this. And so the idea is this can result in avoiding this starvation problem where you have to wind the whole GPU down to do nothing, and then you start back up. An unfortunate problem in the API in the first, I guess, version of Vulkan that had this resulted in insufficient information in the set call, such that it was actually not implementable efficiently. Like you would occasionally find articles that tell you that split APIs in Vulkan solve this problem, but until synchronization 2, I think there was no implementation that actually solved this problem because it couldn't be done efficiently, like it just didn't work out. Or maybe there were some implementations that were and some that weren't. At any rate, split barriers weren't actually a thing that I would even recommend looking at before. Synchronization 2 enhances the set APIs to pass, I guess, like the entire information. I don't know if this thing talks about split barriers. Let's see if it talks about wait. It does. No, it doesn't. Hold on. It's like an advanced topic. Like there's few. I can't find it here right now. But if I go from set event to, so there's set event, which is the previous version, which is insufficient, and there is set event 2, which is sufficient, and they are exclusive. They're like there is set 2 wait 2 and set 1 wait 1, and I think you have to match them exactly. I don't know what the exact rules are. Anyway, and so the idea is that with this API, the driver actually has enough information such that if in this case you use 100 events and 100 sends and 100 waits, then you have a hope to like actually make this work well. Now in practice, I suspect that it's going to be a very bad idea to actually do 100 of these. In practice, I think what might work well is that you have 100 things and 100 things, and you split them in groups in 4 groups or something like this of 25 each. And so you do 25 set, 25 set, 25 set, then wait for the first group, second set of dispatches for the 25, wait 25, wait 25. So like having 100 events is never a good idea, but having a small number of them may make split barriers actually work out in practice. I have not tried this, but this is the motivation, and I assume that people who wrote the drivers for this actually tried this and confirmed that yes, like now it's actually practical to solve these bubbles in this fashion. All right. So that is synchronization 2. It also has some other stuff that we will not talk about. The idea with synchronization 2 is that if you use Vulkan 1.3, you never need synchronization 1, because it's a different API that mostly just makes things better. If you are not using 1.3, then the only reason why you would want to use synchronization 2 API, like if you can't rely on Vulkan 1.3, then the only reason why you might want to use it is because of the split barrier thing, which is esoteric enough that you might not even care. And so then the biggest reason why this API exists is to clean things up and prepare things for the future. But there is one specific benefit in addition to like ease of use that it provides, which is the split bearer optimization. All right, I am officially out of time for all of this. Adam Miller thinks 256 bytes for inline uniform blocks clearly is enough. I don't know if he is right. It's an interesting discussion. I would welcome Adam to submit examples of his shaders where 256 is a good limit. All right, so I'm out of time. I hope there's not actual questions that I have to answer to finish this. Yeah, you can use synchronization to unconditionally, but you have to have a layer, and I don't yeah, I don't know if the benefit, it depends. I think it's like applications that don't target Vulkan 1.3 at all, I don't think it's worth it to actually go and convert to 1.3. The split bearer thing is like complicated. If you actually want to use it, maybe it is valuable, but I think it's more of the case, like with dynamic rendering, I think it's more of a case of do you want to just live in the future but do it today, or do you want to live in the past? And so you kind of decide between those. All right. Buffer device address, by the way, is now required in Vulkan 1.3, which is great, which was a little bit surprising to me, but it's really great news. So we are going to end the stream here today. Thank you, everyone who survived through 4 hours. I don't remember how long 1.2 stream was, but I think it was more than 3 hours. So I guess this is just how much work goes into every Vulkan point release. So there's a lot to talk about. Thank you, everyone. So if you haven't subscribed to my Twitter, you should, because if there is any news on like Niagara on Metal or something like this, it's going to be there. Thank you for the stream. It's going to be on YouTube, and we are done for today.